bored, or frustrated. Once we understand the negative states, such as boredom or frustration, then we had another algorithm in this project which automatically changed the learning materials or adjusted the level of learning challenge to re-engage the students to keep them in a state of flow. The second project was a much more lightweight project based on mobile devices. It was called Pathway Plus. And this is where students with intellectual disability, but mild and moderate learning disabilities, again, had things like their eye gaze and facial features recorded via sensor data. And then we understood whether they're engaged or bored in learning or frustrated. In this case, we didn't have another complex algorithm to automatically adjust the level of learning challenge. This time, we alerted a human tutor with a traffic light system because the human tutor came in to re-engage the students. The next project, AI Top, was looking not just at the learning stage, the emotional stage related to learning of students with autism, but their behavioral states. We know that students with autism sometimes experience overwhelming emotional dysregulation events, sometimes called a meltdown event, where they temporarily lose control of their behavior. What we know is that there are very early warning signals that such an occurrence might occur. And that's called the rumble stage. And again, we're using sensor data and machine learning to predict when those emotional dysregulation events might occur and intervene at a good time with evidence-based well-being interventions. Finally, I'm going to finish with why we should be using explainable AI in light of the vulnerabilities of these students. Just as a background, I'm director of the Interactive Systems Research at Nottingham Trent University. We focus on the development of enabling technologies for the cognitive and physical rehabilitation of users within the real world and promotion of their mental well-being. Obviously, I'm a computer scientist, so I work with other computer scientists interested in human and user-centered design, accessibility, virtual environments, serious games, location-based services, social robotics. But I also work with clinical and psychology researchers. So in terms of clinical researchers, we're looking at electronic health records and automatically selecting patients at greatest risk of a range of cancers from electronic health records. I'm also working with clinicians working with stroke rehabilitation, for instance, using serious games to encourage patients after a stroke to undertake the high number of exercise repetitions they need to do to recover after stroke. So, a bit of background on autism. We know that in the UK, more than 1.1% of the population may fall within the autistic spectrum. In a focused study of 8-year-old children, 3.8 per thousand boys and 0.8 per thousand girls present with autism. And obviously, this is a growing issue. In terms of the UK government, we responded in 2010 with a strategy called Fulfilling and Rewarding Lives. This was replaced in 2014 with the Think Autism strategy, which had 3 main areas of focus: building autism-aware communities, promoting innovation in service provision, and providing integrated care. And obviously, as computer scientists, we're doing the middle one here: innovation in service provision. How we can use the most advanced computer methods to assist the educational and behavioral outcomes of students with autism. And since this is a growing issue, we know that in the UK, 71% of students with autism attend mainstream schools, not special education, mainstream schools. So in light of that fact, it's important to provide students with autism with an environment which is adjusted to their needs and free of emotional trauma. But we know from reports that mainstream schools are frequently neither fully educated or equipped to deal with the needs of the autistic child and give the necessary support, which means, in fact, a large number of autistic children are not getting the educational experience they deserve. Further research by the Autism Education Trust 40% of children on the autistic spectrum in UK schools have been bullied, and 56% of parents of children on the autistic spectrum whose children have been bullied has said it's caused their child to miss school or even change their schools, which means that thousands of autistic children are being illegally excluded from schools. And research by Ambitious About Autism show that 4 in 10 children have been informally excluded from school, at least temporarily, causing them to miss trips, activities, or even just attend lessons on a part-time basis. And obviously this is an unacceptable situation. Research by the National Autistic Society shows that it's not just teachers who feel that the support given to students with autism is unacceptable and not up to standards. 30% of parents feel their child's educational placement is not adequate, and a staggering 70% of those parents are not satisfied with the level of understanding of autism in their child's school. So, given that context, as computer scientists, what are our solutions? So we know it's important to provide students with autism with an environment which is adjusted to their learning needs and free of emotional trauma. And we also know from research in the UK by a leading psychologist, Barry Carpenter, that engagement in education is critically important for these students. For we know without education, there is no deep learning, there is no deep learning, effective teaching, meaningful outcome, real attainment, or quality progress. So our solutions look to use sensor data, which is gleaned from educational platforms, whether that be tablets, PCs, laptops, social robots, all embedded with sensors, including cameras. From those sensors, we can get things like features which are important to engagement and education or behavioral outcomes. These include students' eye gaze, their body posture, their combinations of complex facial features, their interaction patterns, typing or using a keyboard, or even their voice analysis and sentiment analysis. So in Mathes's, this was a very big 30-partner European project, which used both the sensor data and machine learning to understand whether students are bored, frustrated, or engagement, or frustrated or bored. And then when we detect states which are negative, such as frustration or boredom, the algorithm automatically adjusts the level of learning challenge to re-engage them. As I said before, Pathway Plus is a bit more lightweight on a mobile device. Once we detect that students are disengaged, then we alert a human tutor using a traffic light system so that they can come and re-engage students, trying different learning activities. AI Top was looking really at their behavioral outcomes of students with autism. So once we detected a rumble moment just before a big meltdown event, teachers can be alerted and they can try a whole range of evidence-based calming interventions, such as taking the student to a very quiet space in school. These are called the hard space, which is a space where there's very little stimuli. It might be a nice calming area with low lighting, beautiful, nice, calming, relaxing music to calm the student down. Okay, we'll look in more depth at some of these projects and the machine learning approaches we have taken. We know that recent reviews have highlighted an explosion of work in the use of AI tools for education, AI Ed, that detect the emotional states relevant to learning. So whichever approach you're taking, using sensor data and machine learning to say that students engaged, bored, or frustrated, I believe you can do one of three things. You can automatically bring on an intelligent tutoring agent into the electronic learning system. You can alert a human tutor, or you can have another algorithm to automatically increase or decrease the level of learning challenge of the learning materials. In this big Mathesis project, we use both effective state monitoring and the progress of the students, their progress, their learning achievement, to drive the presentation of the learning materials in an adaptive learning system. This was a big project across Europe. We had schools in the UK, in Italy, in Spain, and they're all developing these learning materials, which are learning activities and learning graphs. And the learning graphs were composed of smart learning atoms, which were small, reusable pieces of knowledge, which could be massively variously combined to give the high level of personalization needed for such a heterogeneous population. Then the learning materials were displayed on a variety of platform agents, laptops, computer screens, tablets, or even social robots like the Now robot. And in addition to the accelerometer on the tablet, we also had things like a Kinect sensor to understand body posture as well. So how did we train the algorithms? So teachers who were familiar with the students annotated video recordings of them working on a range of educational materials. So they looked frame by frame at the video and they marked whether the student, in their opinion, was engaged, bored, or frustrated. And then these labels were used to train a range of machine learning algorithms for each individual modality. So for facial features, we used a pre-trained and fine-tuned convolutional neural network to infer emotions from facial images. Eye gaze modality used a two-stream CNN using 3D gaze vectors. Body pose, we used a speed relation preserving slow feature analysis algorithm to extract features classified by a support vector machine model. So the performance of each of these modalities, each of these models, was based on a k-fold cross-validation for the majority of the modalities, but leave one-out cross-validation for the interaction parameters, such as using the mouse and the keyboard. Then to get one value overall of whether the student was the probability of the student being engaged, bored, or frustrated, we used an equally weighted late multimodal fusion scheme using the separate predictions independently inferred by each modality to give an overall understanding of the effective state of each learner. So there was one probability of whether they were engaged, bored, or frustrated. Then, once we understood that, if the student was bored or frustrated, the next algorithm automatically adjusted the level of learning challenge or changed the learning materials to maintain flow. Because we know from the theory, without engagement and learning, there will be no deep learning or meaningful outcome. And we use the theory of, you've probably all heard of this, Csikszentmihalyi's theory of flow. That's our first solution, using sensor data and machine learning to optimize the learning outcomes for students with intellectual disability and autism. But this was a big system. We started this in 2015, 30 European project, 30 European partners, an €8 million project. Big early research in this area. And we faced a whole range of technological challenges, as you might imagine. Second project. After the experience of the Mathesis project, I wanted to scale things back a bit and perhaps get a lightweight system that could work on a mobile device, and I thought really combining the effective state detection with another algorithm to automatically adjust the learning level of learning challenge was very ambitious, and sometimes there's lots of areas in which that can fail. So in 2018, I started scaling back and thinking, can I produce a lightweight system? So in this case, and also there were some problems. When we label the effective state of students using video data, I think quite often those labels were incorrect. Sometimes teachers aren't that experienced with the students they're dealing with. Perhaps they're not the right people to say that student is engaged or bored or frustrated. Perhaps in Asian partner countries, you experience the same problems we face in the UK. We have a high turnover of staff. Sometimes the teachers are very inexperienced. So rather than getting human tutors to assign the labels, which are then used to train the machine learning algorithm, and this time we try to use an independent test to indicate the level of visual attention. And in this case, it's called the continuous performance test. So we know that Swanson's application of signal detection theory gives us quantifiable information about the improvement or deterioration of visual attention in response to a signal. In this case, the signal is a continuous performance test for the classic game Where's Wally, or in the States, Where's Waldo, which is a rapid presentation of screens in which there is a target, and the target is Wally or Waldo. When Michael, real name because he's part of my group and gives permission to use his name, he's a co-researcher with intellectual disability. When Michael is looking for Wally or Waldo, he presses the space bar. And when he identifies Wally, we record his errors and reaction time. And we know that the continuous performance test is a reliable indicator of visual attention because there are significant correlations between its outcome measures, errors and reaction time, and teacher ratings of students' inattention, compulsivity, and I said inattention, compulsivity, and there's very high correlations there. So while Michael's looking for Wally, looking for the target, we have a range of sensors recording his data. You can see in this case, we also use the BCI, the Muse device. We also have a Mitobi sensor there.
Can you hear that, David?
Looking at his eye gaze.
It's audible feedback of when Michael actually sees it before it happens, on when it happens.
So we're recording his BCI. We're recording his eye gaze. We have a Connect sensor. We're recording his body posture, and we're recording his interaction patterns.
You're doing really good, Michael. That was beautiful.
Okay. So the outcome measures, his errors and reaction time, allow us to segment the multimodal data, his eye gaze, his body posture, his facial features, into regions of high and low attention. So we know that when Michael is very attentive, he will make a low number of errors and he will have a low reaction time in spotting Wally and Waldo. Conversely, when he's inattentive, he will have high number of errors and high reaction time. So that helps us to understand the patterns in his sensor data, what his eye gaze or body posture or facial features look like when he's inattentive or attentive. And these provide, we think, much more objective labels by which to provide labels to perform the supervised machine learning method for the data to model boredom, engagement, and frustration. In this case, we used a random forest and sample method.
David?
Hello.
Yeah, you allowed to ask questions interactively. Is it okay?
Please. Yeah, I like a conversation.
Okay. I mean, one thing you mentioned about the EEG, because while working with kids, we know that some of the autistic children, if there is any extra device on hand, on the wrist or on the head, they remove it, they bite it. So how will you deal this kind of things? Because this is the reality when we work with autism children. So
No, absolutely. It's a really good question. So the person I just showed there actually was a person with Williams syndrome, which is a severe intellectual disability. But Michael isn't a person with autism. So when we're working with students with autism, when we started that project, we had a huge interview schedule with students and their parents and carers. And we asked them which devices they might like to wear, which they'd find acceptable or not. And it's interesting because some of the students with autism love wearing watches, especially smart watches, and some of them couldn't have anything touching their skin. So it's not just everybody doesn't want to wear a sensor or all the students do want to wear it. It's a really mixed pattern. So I think the only way we can overcome that is having a multimodal system. So it could be wearables, it could even be a BCI, it could be a number of other unobtrusive sensors like a monitoring device, so that if a student came along and they really liked wearing a smart device, we could use some of that data within the multimodal model. But if they didn't, we could still get data from the other external sources, which are not wearables, to still provide data to the trained machine learning model, which would then still give an inference of their level of engagement and behavior. We can't just rely on any one sensor, such as a watch, because some of the students might like wearing a watch, but as you very correctly said, some of them couldn't have anything touching their skin. Does that make sense?
yes, thank you. So please.
Okay. So in this case, rather than the big Mathesis project, we had a traffic light system to say that with the trained machine learning algorithm, the student was engaged, attentive or not. So at that stage, that traffic light system alerted a human tutor, and the human tutor comes in to re-engage the student, or if they're bored or frustrated, try a different range of learning materials, try playing a game, trying educational materials in a different format. So the first one was a big, basically computer system, complex algorithms. The second one was an effective state detection algorithm, but then a human tutor comes in. Both different approaches. The final project that I'm going to show you today is the AI Top project, and this is specifically for students with autism. Now we know that students with autism show some signs of distress before it's called a meltdown event or an emotional dysregulation event. And you're probably aware that sometimes if students with autism are overstimulated, they'll have a huge event where they temporarily lose control of their behavior because they're overstimulated. But we know that there's a very early precursor to these events called the rumble stage. And cues include the student might start rocking and biting themselves, scratching, kicking, banging their heads, or even being violent. So there's quite a few researchers starting to build up research works which show that if we can use these behaviors captured on a range of devices, sensors, including cameras, but also bodily worn sensors, and deep learning, we can predict meltdown events before they actually happened at this very early stage, the rumble stage, and then introduce in a timely fashion evidence-based calming interventions, well-being interventions. So at the school I work with, when a student's getting aroused, it's called a heart space, which is a very dimly lit space, lots of nice cushions in, fidget toys, beautiful music, calming music. But other students prefer using a fidget toy. Some students like playing a game or doing some really exhausting playing like football or cricket, which really calms them down. We know that for a machine learning classifier, the most important features or modalities in decreasing level of consistency would to indicate the start of a meltdown event would be covering ears, covering the face, biting hands, or flapping hands like that. So what work are we building on? We know our researchers, Patnam in the States, as early as 2017, was using a deep learning approach to understand meltdown events in students with autism. They use teachers and parents to look at the video data, individual frames of students approaching a meltdown event. And again, that's an ethical issue. How do you really naturally record students approaching a meltdown event? And that's a difficult one to deal with ethically. But they were annotating the individual facial features of students on this video to indicate and to label the rumble moments. Then those labels were used to train algorithms such as deep recurrent convolutional neural networks to infer emotions. And in their case, the RCNN compares loss and accuracy at each layer of the neural network and adjusts the learning rate appropriately. And the choice was based on robustness, compactness, and reliability. And then evidence-based interventions, well-being interventions, can be introduced in a very timely fashion at a very early stage. And these are things like, as I talked about before, playing with a fidget toy, doing some exercise, deep breathing as well works with some students. So just a little bit on their method here. So the neural network was trained for two modalities, covering ears and covering face. And obviously, as you all know, we need both positive and negative examples per gesture. So sometimes students touch their face and it means they're approaching a meltdown event, and sometimes we're just touching our face, aren't we? So obviously I'm preaching here to a range of people who've got high expertise in machine learning. But the data set, for instance, for covering ears was fetched a neural network model for the two classes, and you needed around 1,000 pictures per class of both negative and positive examples, and a validation set of 15 to 25% of the database was kept for validation, and that led to a decreasing training loss and an accuracy of around 93%. So quite high levels of accuracy there. We took this project and took this early research and created a big European project, which started 2 years ago, and we have 1 year to go. And if you're interested, I can give you more information about this project later on. Just contact me on the email address that you'll see at the end of this work. But in order to continue to do work on this project, we're starting to form an action recognition model. So we have our first version of the action recognition model, which is trained on data for touching face, touching ears, rocking, flapping hands. And then we want to not just have the visual data, we want to combine that with physiological data, which includes heart rate variability and also galvanic skin response, but also potentially compound and basic emotional features of the face as well. Additionally, the requirement for a large training data set could be addressed via one-shot learning, where we aim to learn information about object categories for one or a few training samples. We have other work in the field where we built a stress detection model for students with intellectual disability, where we use transfer learning, where the convolutional neural network is initially trained on a very large data set, and then the last fully connected layer was removed and trained on the target data set for those students who undertook a stressor experiment, but that was simply doing simple mathematical problems. But that removes the need for a very large training data set. And actually, when we did that, we had some very good results. We know that individual differences, such as autism, limits the generalizability of machine learning models to infer emotions, because we know that anyone's physiology varies greatly when experiencing the same emotion. But when we use transfer learning for students with intellectual disability, we improve the performance of our model from 82.5 to 93.9% in modeling psychological stress. So with this system, we intend to have an action recognition model, but it's multimodal, augmented by physiological data, which includes a heart rate variability, galvanic stress response, skin response, sorry, and a range of other modalities to get a very accurate, but as you rightly pointed out, multimodal model. So if a student wouldn't wear one of the sensors, such as a smart watch, the system would still have other modalities that it could rip data from and still feed into the fully trained model to still give a reliable interpretation of their level of psychological arousal. So with these tools, which look at sensor data and machine learning to understand the emotional states related to learning and behavior, we provide personalized learning pathways to support any student with intellectual disability and autism, and provide a learning environment which is free of an emotional trauma. And this is increasing the likelihood that these students will make both the academic and social progress that they should do. But if we understand and decrease the frequency and intensity of meltdown events, it will lead to improved mental health for that student and hopefully decrease instances of absenteeism and bullying, and also help prevent the secondary consequences of their difficulties, which can, if unchecked, can lead to anxiety disorders and depression, and potentially improve the level of understanding of autism both within school and in the wider community. Now we're coming to nearing the end of the 45 minutes, so I just want to finish off with a note about why we think at NTU explainable approaches to supporting students with autism are very important. We know black box models are difficult to understand and interpret, and that's just even for the people who created them. And this is especially the case for neural networks. Hundreds of hidden layers, millions of signals that are extremely difficult to reconstruct. And it's essential that the decision-making process is transparent and clearly understood in a range of areas that I work in. So I work in looking at codified electronic health records from GPs to identify patients at greatest risk of, say, lung cancer. Because we know that when lung cancer is detected because it becomes symptomatic, that's usually too late, unfortunately, for the patients. If we can use codified electronic health records and push that envelope a bit earlier, 3 months earlier, 6 months earlier, by automatically selecting the patients from electronic health records, the outcomes, the health outcomes for that patient might be much better. Again, we're using sensor data and machine learning to understand the behavioral states of students with autism. We really need to have a level of transparency or trust in those algorithms because we're dealing with highly sensitive populations. And we know from research in the Lancet that transparent algorithms or explanatory approaches can make the adoption of our systems, AI-based systems, less risky for clinical practitioners. And I think that's also for people working in special education with highly vulnerable students. I mean, that explainability is not just measured solely in terms of algorithmic difficulty, but also in terms of accountability, security, and responsibility. And our approach aims to shed light on 3 processes of machine learning methods: data analysis, model assessment, and production monitoring. And some of our latest work shows an AXI pipeline for autism support. And in this case, it's autism detection as well and diagnosis. So just lastly, how might we do this? We know that federated learning is a big hot topic. I'm sure you've got many presentations on federated learning. But it might help us with data privacy, because we know it helps each organization to keep its own private and secured local data. and provides flexible models and solutions to manage real-time data using a combination of offline and online processes. So the local models are trained on the local data, and then the weights of the models are shared with the global model. And it preserves data privacy and addresses these concerns related to the use of behavioral and health data, whereas traditional methods perhaps use centralized machine learning and don't include these benefits, and present a higher data breach risk and require transfer of large files. So obviously, like a lot of you people at the conference, we're looking at federated learning to help us with data privacy in very sensitive areas. So, affective state can be monitored in students with autism and intellectual disability using a range of platform agents and sensor data and different machine learning models to understand states related to learning and behavior. And if we understand states related to behavior, we can certainly support students at a very early stage before a big meltdown event happens. So that improves their mental health because there's less frequent and intense meltdown moments, but it might also improve the level of understanding of autism in school and beyond school because these are ubiquitous tools. I want these tools to be not just in the classroom, but at home and in the community too. We know that transparent algorithms or explanatory approaches can make the adoption of AI systems less risky in clinical practice, but also in educational practice, especially for students with autism. And we know there's a federated learning is at the moment a really good candidate for preserving data privacy and addressing the concerns related to the use of behavioral and health data. If you want to contact me, my name should be somewhere on the website. We have a range of projects with Asian partner universities at the moment, including Diverse Asia, which is introducing accessibility practices and personalized education into higher education and Asian partner universities to promote the inclusion of students with learning disabilities and other disabilities and higher education. And thank you for listening today. Thank you.
Now I request
Okay.
Yes, thank you very much, Professor Sharat. Are you here? Okay. Now, if not, then just when he will come, he can address as well. So I have a few questions because this is a question at a time. So if anyone has any question, please raise your hand or type your question. But we don't see anything now. But David, I mean, this is a definitely a fascinating presentation and excellent works on this topic. And I have been working on autism since long and human activity behavior on sensor data, skeleton, and others. So in one of the works, which is more related to your work, is related to 61 children from ages 3.5 to 6 years old, based on basically Norway and Finland. So what the work is about and we have published and we are working on a few projects at the same time, that a robot enhanced therapy, like instead of regular therapy by therapists, because you mentioned that therapists can be weak or very good. It can vary, but if we have a system, that is important. So robot enhanced therapy, can we do something? So when we do that work, it's a problem that you are using Kinect sensors or Azure Kinect, for example. We are also exploring that. But lots of the noises, this is the problem, because you just get the upper body and only on the sitting position. But the kids don't just remain on the sitting position most of the time. So what are the issues you are thinking with that? And especially your setup and our setup as well. I mean, when we do, like you sit in front of a robot or some system or camera and sensors, then you get the data. But if the location of the data is changing, if the chair is moving, or if I'm looking at different directions, my head and gaze. There's a difference. So how are you thinking? This is one, and how many kids roughly you are exploring in your project so far? Thank you so much.
Yeah, so it's a really good question. So we started simply, like you, looking at just the students sitting down, working with the education materials, a robot or a PC. But now the action recognition model is a one that can also sit in the classroom and understand students in a more mobile context. And that's the one we're working on now. We're working with a really good machine learning specialist who thinks he can solve that problem, but I think we should communicate after this as well. If you please get in touch with me and share your experiences. That would be so valuable. And I can tell you how now we're moving on, not just have a really constrained model, looking at the student working on a learning platform, but a more unconstrained model. And I can tell you how we're starting to do that. But it sounds like we're doing work in very similar areas, and I would love to share our experience. So please do contact me after this.
So, may I ask you one question?
Dr. Muni, please.
Okay. Thanks, Professor David Brown. Actually, it is a nice presentation. So I'm actually working on the autism spectrum disorder kids, a research area. So actually my question is different. I found that not only me, also people found that, so this is like a spectrum disorder. It's not a single disease. There are many different types of condition could be included. The behavioral pattern and even the symptom and sensitivity and sleeping pattern, many variables are different for, actually it's kids to kids different. So in this case, what is your strategy to consider in the development of algorithm?
Mohammed, that's a great point. So there's even I wouldn't even call autism a disease. We have a social model of disability rather than a medical model. So I very much work in a school where we have social models of disability rather than clinical models. And obviously autism is a huge spectrum and a range of subtypes as well. So luckily, I work with people at UC Davis in the States who are specialists in autism. So in this project, we're working with students who have a dual diagnosis, school-age students of autism and intellectual disability, and quite a narrow age range. But you're right, our experts in autism keep us very well defined. If we're going to define a solution, be very definite about the subtypes of autism you're dealing with. And so it's really important, man, because I'm a computer scientist, so I'm not trained in neuropsychology. So my strategy there is within a team to have a very multidisciplinary approach, which I talked about at the beginning. Our expert is a woman called Bonnie Connor, who's an international recognized expert in neuropsychology, autism, ADHD, and she will, in any design that we do, which subtype of autism are you talking about? Define the age range. Specifically, the school I'm dealing with is usually mixed learning disability and autism, but with a primary diagnosis of autism, but usually with an intellectual disability too. I tend to work less with students high functioning.
Yeah.
Myself.
Okay. No, thanks. Actually, when we are looking about the types of like the pattern of behavioral or other even socialized behavior, then we found that it is not same, even the male and female, even the age group, even for the same age group, there is a difference, huge difference. So, and even the same type of intervention does not work for the all kids. So that is really difficult.
Yeah, that's really important. Absolutely. So what we do is have a multimodal system. We recognize the population we're dealing with is extremely heterogeneous. So it has to be multimodal so that if a student doesn't want to wear a wearable sensor. We have a range of other areas by which we can understand their arousal. Plus the system is trained. We collect our own label data set from hundreds of students, from a wide range of different subtypes. In addition, the interventions are varied too. So if we understand a student's becoming aroused, there's a whole compendium of interventions, and the tutor chooses the one that they know works with that student.
Okay,
Some
thanks.
students like to play fidget toys, some like to go to heart space. I work with people in education, so I don't know if you sometimes remove your students when they become aroused. At school, we take them, it's called a heart space, which is a very quiet, I think a really peaceful space with low level lighting and music. But I work with people who argue that that's exclusionary and we shouldn't be doing that to students with autism. And that also emotional dysregulation, we don't see autism as something that needs to be fixed. We don't have that model. So I'm working with very radical people in autism who autism isn't a disease. It doesn't need to be fixed. Sometimes students with autism need to express their emotional angst, and perhaps removing them to the quiet heart space isn't a good practice either. So in my teams, I'm hopefully best informed by people working neuropsychology and education too, because I'm only a computer scientist and I only know about the really computer methods. But it's a great conversation.
Yeah, thank you, David.
Okay, thank you
As
so
well
much.
as Muhammad Ali Mooni and myself, we are all computer scientists, and so we are not. But we are also working on autism so that we can contribute and so on. So that's wonderful.
Can I
So
ask you
thank you
both
so
to
much.
please contact me on my email address and share your experience with research? I would love to hear from you more.
Yeah, so I thank David Brown for his scintillating presentation. Amazing work indeed, and lots of great projects. And I find it very interesting because I have been working on the similar areas since long. So that's wonderful, and I hope that I'll contact with you and have more discussions so that we can learn from each other and do something together and try to help the future, especially in developed world as well as developing countries, because the perspectives in developing countries are different. So with that, I would like to thank the organizer and to have a great professor like David Brown as a keynote, and thank him for his time in the early morning in London, England. He's in Nottingham. I shouldn't say London. So at this moment, I'm in London, by the way. Organizers, I mean, if you have any formalities, because we have online quest at this moment, we would love to have you in Bangladesh in the future. I'm a Bangladeshi, by the way, so it's a great honor.
I'm coming to Bangladesh in January for our Diverse Asia Project meeting with Mufti Mahmood. Yeah, so Shaman Kaiser. So I'm going to be there on 2nd of January in Bangladesh.
Oh,
Okay,
great.
let me see you.
Shamin Kaiser is another, I mean, he's my younger from the same department in Bangladesh.
So I'm going to be visiting Shaman Kaiser in January.
Yeah. Okay.
Thank you so much. So from the organizers, please share your next formalities. So David, if you just unshare the, yeah, that's wonderful. Thank you.
Okay. I'm going off now for breakfast.
Just 1 minute. I mean, David, we have just the
virtual
certificate on place. Yeah.
Hello.
Hello.
It's a very honor to our David Brown sir to have to communicate with you through this session. Thank you very much to our session chairs and session moderator. Now I want to share something to our David Brown sir. Let me share the screen. This is for you, David Brown sir.
Thank you very much. Thank you.
Okay, thank you so much, Professor David Brown sir, and rest of the audience, please wait for the next session. The next session will be started at 3 p.m.
Davis, thank you so much, and we'll be in touch and keep going on the great works. Yeah. Bye-bye.
Please keep in touch, and I look forward to coming to Bangladesh in January.
Yes, yes, and I hope to see you there. Who knows?
Yeah.
Bye-bye.
Okay.
Yeah,
Bye,
thank you.
everybody. Bye-bye.
Bye. Bye-bye. So our next speaker, Dr. Bala is here. So thank you so much. And of course, Professor Pietro is here. So welcome everyone.
Good afternoon.
And Professor Siddiq is here as well.
Just let me know, Bala is my friend. So,
but Bala looks very, very young than you, sir.
Bala. So, Bala, welcome to Bangladesh. So this time, say in cyberspace, but in future, in person in Bangladesh.
Sure. Oh, so definitely. In 5 minutes. Just if you need to take any coffee or something, and so we'll be back within 4 minutes. Yeah, and then Professor Bala will start, and afterwards we have another amazing speaker, Professor Pietro Leo. We are having our friends in the same frame. This is the beauty of online at this moment, and that easily we can connect many people. Yes. Like. Professor Nazbu Siddiq and Ali Muni is from Australia. Is it midnight now? No.
No, it's evening.
Right,
7 p.m.
All right. Okay. Wonderful. Thank you. So I'm just taking something and then be back in 4 minutes and then we'll start. So, the organizers, you can stop the recording so that you can restart, when we start the next session. Thank you. And Dr. Bala, you can just try to share, just to see, check, as you were here.
I'll do that now, yes.
Thanks for the invite. Let me know if you can see that.
Yeah, it's okay.
Yes, yes. Okay, perfect.
Yeah, it's clear. Yeah. Yeah, thank you, Bala, for accepting the invitation. I know you are very busy, but
not on a Sunday.
This is how it is.
So not on a Sunday. So it's perfect timing for me. I've been traveling loads recently, and then that's why you hadn't gotten a reply. But since the pandemic came and went, well, it hasn't fully gone, right? But the borders have completely opened, and I've just been on the road for weeks and weeks and end.
Yeah. And so we are back on campus. It looks very funny. I feel it's a funny feeling. Just I can see the people, and myself, I am having a bit of problems. So sometimes I don't hear people clearly because I have been using the earphone for over 2 years. And when they are really speaking, so it takes me time to identify, right, who is calling from which direction. It's really difficult.
Got you. Yeah, we've gotten used to doing all presentations online, right? It's set a new standards in the way that we share. That's what I find. The amount of webinars that we have, it's so much easier to share. But then there's also there's an upper limit to what people will when you have something virtually. You find that there's a whole group of people who are not actually focused on the event. So unless they've taken the hour off, to listen to you, then everyone's multitasking, right?
Good note.
Exactly.
If I'm not disturbing you, good note to all. I'm the session coordinator from MIET 2020 from NSTU.
Okay. Thanks for having us.
Sir, can you hear me?
Yeah.
Yes, we can, yeah.
Thank you all. Sir, we are going to start our keynote session 8. Our session title is Accelerating Industry 4.0 in Manufacturing Through Data and AI. This session will be conducted by Dr. Bala Ambashi, Global Technical Director, Databricks. And for this session, sir, we have session chair, Professor Dr. Atikur Rahman Ahad, University of East London, UK, and session moderator MD Wahidur Rahman, NSTU Bangladesh. Without any further delay, I am requesting the session moderator to introduce our session chair and all session chair. Thank you, sir. Thank you to all.
Thank you so much, our program coordinator. So welcome to our keynote session 8. Our session title is Accelerating Industry 4 in Manufacturing Through Data and AI. It is conducted by Dr. Bala Ambasi, Global Technical Director, Databricks. Here in this session, we have the session chairs, Professor Dr. Atikur Rahman Ahad, University of East London, UK, and Dr. Mufti Muhammad, Nottingham Trent University, UK. So I would like to request our session chair, Honorable Professor Dr. Atikur Rahman Ahad and Dr. Mufti Muhammad sir, to conduct the session. Thank you.
Thank you very much. Welcome to this keynote number 8. We have a distinguished speaker, Dr. Bala. He will deliver on accelerating industry 4.0 in manufacturing through data and AI. So it's a very well fit topic for this conference. And Dr. Bala is the Global Technical Director for Manufacturing Logistics at Databricks. And he has a huge experience over 25 years in this domain, data analysis, AI, and machine learning. And actually, he was the head of AI at Stanley Black & Decker. And not only that, he has been serving the research community, IEEE societies, and he served as the chair. He's basically at this moment the chair for the IEEE SMC Society, which is one of the largest societies of IEEE in UK and Ireland. And he also serves as an industrial advisor to the EPSRC. All the researchers in UK, they are just looking at EPSRC for funding and other things. So we are delighted to have Dr. Bala in this talk, and I'm eager to listen from him along with others. So please welcome Dr. Bala for his talk. And if you have any questions, as you know that you can just write down in the chat box, or later on you can ask. So Dr. Bala, the floor is yours. So thank you so much. Please start.
Thank you so much for having me this morning, and thanks for the introduction, Professor Atikur. Really pleased to be here this morning. I will be talking along the lines of industry now. I'm going to give you an industry view of how we see data and AI. And it's not typical of your academic conferences, right? I know that you all love equations. We love equations in industry as well, but the difference is that we want to apply these equations and get business value out of it. And that's the objective of industry. So I'm really happy to be here today, both representing the profession, but also being able to share my views with you on where we're going with Industry 4 and manufacturing. So as a matter of agenda, I'm going to talk very briefly about where I come from, the company that I work for, just in about 5 minutes. And then I'll speak to you about some of the manufacturing trends that's out there. I'll speak to you about a new architecture that we've developed called the Lakehouse architecture, which is basically accelerating the adoption of AI within industry. And finally, I'll speak to you about Spark. So Spark is a software package that is at the core of Databricks. It's something that we invented. And I'd like to address that and how we are able to scale compute and why this so huge adoption of Spark within industry and academia as well, to be fair. So Databricks is a company. We define ourselves as a data and AI company. We are a startup based out of San Francisco. I myself I'm based in London, although I look after manufacturing globally. We are 4,500 people, right? And we are expanding hugely. We hope to be 10,000 people by the end of next year. So we are hiring very rapidly and we are growing rapidly. So when we define ourselves as a startup, we are not quite the size of a startup. We are one of the biggest startups in the world, and we are one of the fastest growing startups in the world as well. We are invested on, we are privately invested on. And what's unique about Databricks as well, we are also invested on by the three main cloud providers, right? So Microsoft Azure, Google GCP, and Amazon AWS. And I think we are in a unique position where we are the only company that has been invested on by the three cloud providers. We have over 7,000 customers globally. We work with half of the Fortune 500 customers. We work in healthcare, financial services, retail, CPG, and manufacturing, of course. And manufacturing is an area that I lead within Databricks. So the size of our portfolio is huge. We've got over 1,000 customers in manufacturing. We tend to divide them into these segments. From automotive, we work with companies like Daimler, Toyota, and so on. In aerospace, we work with Airbus, Boeing. In the industrial area, we work with Rolls-Royce jet engines. I'll give you a use case later. Shell in oil and gas, BP in oil and gas, and so on and so forth. So quite a hefty portfolio. If you do follow the Gartner Magic Quadrant, the last one was released in 2021. We were defined as one of 4 leaders in data science and machine learning. We were also classified as one of 4 leaders in the cloud database management systems, right? So in the first category, it's our competitors are like H2O.ai and DataRobot and so on. In the second category, our competitors are actually the cloud providers who actually invested in us. So all 3 of our investors are also in a way competitors, but we work very closely with our cloud providers because when it comes to big data, then Databricks is called in, right? So Databricks launches about 11 million virtual machines a day on the cloud in order to serve our customers. So one of the differentiating factors about Databricks is that we are huge proponents of open standards and open source. Here I'm listing 6 core packages. We've actually got a 7th core package, which is open source. We see more than 50 million downloads from our open source packages. The biggest of this by far is Apache Spark. So Apache Spark is a technology that is developed by Databricks. We open source it, and we see about 35 million downloads a month now. The other one that may be familiar to you is MLflow. MLflow, if you are deploying machine learning, then you may come across MLflow. And the vast majority of machine learning algorithms today deployed globally is through MLflow. 2 or 3 years ago, we released the standards for Delta Lake. Delta Lake is a lakehouse architecture. Unlike data lakes, unlike data warehouses, we brought it together. So I'll say a little bit more about it. So we have a huge community behind us with Databricks, but we also package all of this into a managed services platform, and that's how we do business with our customers. So open source, open standards, the core foundations of Databricks. And the DNA of Databricks is this: we were founded by 7 academics from the University of California, Berkeley. Our CEO, Ali Gotzi, is still an academic in very many instances. They are all still publishing papers and all that. The first core technology was Apache Spark. I mentioned Delta, MLflow. In 2020, we released the Photon engine for SQL queries. So if you wanted to do large-scale machine learning and you wanted to be able to query huge data sets, then this is where Photon comes in. And I'll show you the outcome of where Photon has taken us in the last 2 years. But essentially, the whole history of Databricks is that of, as I said, open source and the ability to enable our users to go and develop AI solutions very quickly. So the idea is to accelerate the adoption of AI by lowering the threshold to entry. And as I said, our founders are still publishing papers. People like Reynolds Shin and Mate Zaharia, who are still academics. I believe Mate is an adjunct professor at Stanford. And in recent months, in the last year, we've taken the world record for TPCDS when it comes to data performance at the ACM SIG mode. I'm sure you know the ACM organization. They gave 2 awards this year to Apache Spark and Photon. So Apache Spark won the SIG mode Systems Award, and Databricks Photon was awarded the best industry paper. So that's a brief introduction to Databricks and Spark and all the technologies that we developed. Now I'll walk you through some of the industry trends that we are seeing across the globe when it comes to manufacturing. And manufacturing tends to be a slow-moving kind of industry. If you look at the investment that goes into manufacturing, it tends to be longer term. You know, when you put equipment on the shop floor, the equipment will last for 10 or 20 or 30 years, right? If the system does not break, you wouldn't replace it. If the system needs to be serviced, you'd service it. but essentially the investments are long-term, right? So in which case as well, when you talk about the agility to do change management, it is a factor, right? If it's something that is producing revenue, would you break the system? And the normal answer is you wouldn't, but could you do it more efficiently? Now, the manufacturing industry is undergoing a change, and a lot of it is due to external forces, right? We know that the most competitive kind of companies are driven by data and AI. And I've spent the last 15 years working in industry. I worked for 10 years as an academic and the last 15 years in industry. And the companies that I work for, they've all had the vision of being a data and AI company. I worked for companies like Procter & Gamble for 10 years. I worked for Stanley, where I was the head of AI. And the idea is to convert the thinking of the company to invest in digital transformation, to accelerate the take-up of digital, and to deliver value from data and AI, to build new products from data and AI, to do service and maintenance based on the advice that data and AI gives you, essentially to be a data-driven company. And the four forces that is essentially driving change within manufacturing are these. Firstly, that there is a production and workforce gap. That there's also a skills gap when it comes to manufacturing. So, for example, when many of you are students at the university, when you graduate, the first port of call may not be manufacturing. I guess what we're trying here to do is to lower the boundary for threshold. If you are into data science, how do you use tools that does not need you to be a software engineer, for example? If you are a data scientist, be a data scientist. Don't be a software engineer. If you are a real-time engineer doing streaming pipelines, be that. But don't become a data scientist or a software engineer. And building tools in order to ensure that you can excel within your profession is extremely important. More so in manufacturing when you get the specialized resources that are working on things. And manufacturing is one of the fastest growing verticals. If you look at the latest study that we did with the MIT Technology Review, manufacturing is up there with retail and CPG. The investments going into manufacturing is as high, if not exceeds some of it going into other areas. So you can see that manufacturing is really getting it and adopting the technology. The second thing is supply chain volatility. And there's many things. There's a war going on, there's a pandemic and so on. There's a chip shortage. And how do you apply AI? How do you do forecasting at scale? How do you do per-SKU forecasting? How do you do part-level forecasting at scale in order to accelerate the adoption, to give you both accuracy as well as the ability to track through an external phenomena like the pandemic? You know, how do you get performance in order to run these algorithms? Thirdly, there's a need for additional sources of revenue. And many of the companies that we work with, they're looking at equipment as a service, right? Moving to an as-a-service model. So you buy a piece of equipment and you subscribe to a software service, essentially, so that you have this one-to-one connection with your customer, such that you pull revenue in. So they take out a subscription for what they need. You maintain that connection with them, and you develop to their need. In return, you provide the uptime, which is guaranteed, right? So instead of you buying a CAPEX piece of equipment, you know, where it's capital expenditure, large piece of equipment, let's say to do semiconductor lithography. Instead, what you do is you buy it as a subscription model. The supplier guarantees the uptime, and you only pay for the products that you build. And finally, sustainability is a huge focus of manufacturing. So we've got some of the biggest polluters within manufacturing. And it's really important to meet regulatory standards. But to many of these companies as well, when they run optimizations, they have to, they're thinking about the bottom line of the company. So how do you actually save on cost? For example, if energy consumption is a big issue that leads to greenhouse gases, can you reduce your greenhouse gases, but can you also at the time reduce energy consumption? We work with some of the largest shipping companies in the world where they're doing things like route optimizations. They're looking at ways to reduce that fuel cost, because fuel is one of the contributors to greenhouse gases. So very important within engineering, within manufacturing. And of course, we can't escape talking about Industry 4 when we're talking about manufacturing, right? But this slide, I just wanted to highlight that we are midway through Industry 4. Industry 4 was launched by the German government in 2011. and it's expected to continue up to 2030. So we've got about 8 more years to Industry 4. And so when I speak to people, I say, let's talk about Industry 4, but let's also look out for the lighthouse that's in Industry 5. Industry 5 specifies a fully interconnected ecosystem. The World Economic Forum at the moment is working on a standard for Industry 5 that also brings in the people element of Industry 5, right? So do not ignore your workforce, right? Part of ESG is ensuring that you have a workforce that is able to be part of the ecosystem, and that's extremely important. But if you look even at Industry 4, you get all kinds of maturity. On one end of Industry 4, you get brownfields. Companies that are 100 years old who have been building equipment for the last few years based on legacy equipment that's not connected. You don't have sensors, you don't have IoT. And that's the challenges that they're facing. On the other hand, you've got greenfield where it's a fully modern environment. So in this case, we need to help organizations to think big and also to think for the future. If they're going to be putting in infrastructure investment, how are they going to be using data and AI in the future? How are they going to be using it 10 years from now and 20 years from now? And what kind of technologies? It could be 5G. It could be some AI algorithms that consumes a lot of data. So what kind of architectures do you need to be able to serve that industry? And some of the key trends that we are seeing, and I actually look after manufacturing and logistics globally for Databricks. Some of the key trends that we are seeing across the board are these, right? The first one is edge to AI. For manufacturing, edge is very important. Some of the decisions are made on the shop floor itself, the manufacturing shop floor. When we work with autonomous vehicles, like companies like Rivian and Zoox and Arrival, there are decisions that has got to be made on vehicle. So the trick there is that how do you train models at scale and deploy it to these vehicles? And the way to do it is through the cloud, in which case you need to subsume a lot of data, train the models at scale using GPUs in the cloud, and then pushing it back to the edge models. And why do you run it on the edge? If you've got a vehicle that has to make a reactive decision to do obstacle avoidance, you'd want to make it on the vehicle, right? Because there's a huge latency to the cloud. In supply chain, we are looking at fully interconnected ecosystems where companies are no longer looking at their four walls of the business. They're looking wider than that, looking for external data sources, looking at freight logistics, looking at loading data sources and all that. But how do you subsume this huge ecosystem of data on the one platform? And that's extremely important. One of the key technologies being developed at the moment is called the data mesh. And I encourage you to look at it. And what we are trying to do is to offer one part of the data mesh through the Lakehouse architecture. Digital twins is another big one, where you want to be able to create a virtual environment of your, let's say, your manufacturing shop floor, your equipment, and so on. Why? Because you want to be able to run predictive models on it and make recommendations. So for example, if you need to optimize a power plant, you would be essentially running the models in the cloud, making the recommendations and feeding it back to the digital twin, and the digital twin essentially feeds the information back to the physical system, which is the physical plant. Extremely important because you can run thousands upon thousands of models virtually without actually stopping production or stopping the generation of electricity or stopping the vehicle or anything like that. So the digital twin operates in parallel with that. And one of the biggest use cases in manufacturing is predictive maintenance. And we talk about predictive maintenance a lot. It's about time series, it's about anomaly detection. The trick here is that how do you do it at scale and frequently enough? And that's where things like the Spark engine comes into play. And finally, data collaboration. The ability to collaborate across organizations, the ability to collaborate across organizations is extremely, so within and across organizations is extremely important, right? And for that, you need data governance and things like that. So what we've seen in the last 10 years is the democratization of data across the manufacturing industry. When we used to talk about manufacturing, we used to talk about the business end of data. So the enterprise resource planning part of it, how do you source raw materials? How do you plan your workforce? How do you do warehouse optimization? How do you build supply chains? That's the management end of things. But in the last few years with IoT and things like that, industrial IoT, we are doing so much more at the bottom end. So looking at sensor data, looking at MES data, looking at SCADA historian data, moving it to the cloud and doing the predictions in the cloud, doing the computes in the cloud. And what we are seeing now at the moment is, you may have heard of this term, IT-OT convergence. So IT coming from the top, with business data, OT coming from the bottom, operational data coming from the bottom, and converging into one platform. So being able to do that on the one platform and being able to, say, do demand planning at the top, while knowing how much production you're backfilling is extremely important. And that's where you have IT-OT convergence. So the full trend is that we are seeing data across the ecosystem. In the past, when we spoke about manufacturing, we talked about raw materials being manufactured, being finished goods, being transited. Now we are talking about data flow across the organization. But manufacturing is struggling with data and AI. For a start, I spoke about legacy systems. When you've got legacy systems, you've got siloed data. You've got siloed data from different machines not being shared. They may not even be connected. We work with many customers where their shop floor is not connected to the internet. They've got an intranet flowing. You've got this inability to scale enterprise data sets, especially when it comes to IoT data. Machine data, you're talking about a different scale of data here, right? You're talking about petabytes of data. Where do you store it? You do not store it on premises. You should be storing in the cloud where cost is cheaper. You need real-time insights. And case in point is that when you do efficiency and performance computations, many organizations report an OEE score, an MTBF score, and stuff like that towards the end of the week. When the production is done on the Friday, these values are computed. You want to be able to do that live. And finally, there's an element of intellectual property, because we understand that data, which is owned by companies, there's an element of intellectual property there. It tells you how to build a product. It tells you how to create a product, like, let's say, a shampoo, where you're doing process optimization in order to get the right outcome. There's a lot of IP there. So you need data governance, but you also need to be able to share the data at the same time, which is absolutely conflicting. And that's where it leads us to what's known as the lakehouse architecture. So we didn't coin the term the lakehouse architecture, but it's something that we are the first developers of the lakehouse architecture. This slide essentially tells us that what's been happening in the past. We are huge fans of statistics, but we've been using statistics to do things like this, to do reporting, ad hoc queries, data exploration, and so on. So essentially looking backward in time, trying to measure the performance, the past performance of things. But some of our most innovative customers are working at this end of the pipeline, trying to do predictive modeling, trying to do prescriptive analytics, trying to do automated decision making. And we find that companies that are more mature with a digital transformation kind of view of the industry will be investing in this, will be investing in machine learning, will be investing, of course, in statistics as well. You can't get away from statistics, right? Statistics is absolutely foundational, right? But investing in machine learning to make that difference, so to make it more predictive. And many organizations that you see today, they are conflicted. They've got data warehouses to, these are like your SQL databases, right? Very powerful. I'm sure you're familiar with things like Postgres, MySQL, the Oracle databases, and all that. And these are essentially data warehouses where you do historical reporting on the data. And it's fine to do historical reporting. The good thing about a data warehouse is that you've got performance, you've got atomicity of queries. So you've got a lot of protection when you do it in data warehouses. But when you work on machine learning, you need what's known as a data lake. You've got structured, unstructured, and semi-structured data going in. The problem there now lies in the fact that when someone wants to do machine learning, they'll be working in this environment. When they are working in reporting, they'll be working in this environment. So you get data that's being duplicated out of the warehouse to the data lake, so that you can train your light GBM models or your XGBoost models or your deep learning models, right? So data duplication is a huge problem. The other problem is that you can't actually run workloads that require you to do reporting on the data lake, because you don't have performance. A data lake is essentially like an S3 bucket or an ADSL bucket that you use in the cloud, right? It's a file system. There's no governance of the file system. Anyone can access it, or you can put restrictions where no one can access it. but then you can't run business workloads on it. And these are essentially the challenges, right? So data gets copied all the time. You've got different governance models. On one end, you're doing business intelligence and SQL analytics at the business end of things. And then on the other end, on the data lake, you're doing data science, machine learning, data streaming, and all kinds of things. And so what we need to do is to bring it together. And that's where we've come up with what's known as the Lakehouse platform. And the Lakehouse platform is quite unique. It combines the principles of data lakes and data warehouses in one. We can actually input unstructured, semi-structured, and structured data. So you can also have warehouse workloads on a Lakehouse architecture. But in this case, because we built it over Spark, it means that you have the performance of Spark, and you can run machine learning workloads. You can run SQL workloads if you want. So if you wanted to, for example, do an atomic transaction, you could in a lakehouse, which you couldn't in a data lake, you could in a warehouse. So combining the best of both worlds. Now, the detractors will tell you then that we wouldn't have performance. Fortunately, we've hired some of the best people in the industry. And at the moment, we do hold the world record for the biggest data sets out there, the TPC-DS benchmarks. So for the first time, a data lake kind of architecture, which is a lakehouse architecture, is holding the world record for the data warehouse. And the reason we've built this is basically to run AI machine learning workloads. The ability to scale these workloads and to run these machine learning workloads. The technology that we've developed is called Delta Lake. And up to about July, it was about 80% open source. In July, we announced that it's now fully open source through the Linux Foundation. So Delta Lake is now today a fully open source project within the Linux Foundation. I encourage you to look at it. So I've been talking about Spark. I'm just doing a quick time check, right? So I should be able to be okay, I believe. So I mentioned Spark as a core foundation, founded by our founders, right, of the company. Spark is licensed under the Apache license, right? So we've got an open source version of Spark. And if you do use our competing technologies, Apache Spark, one thing, is so prolific within the industry, right? It's basically the main compute engine when it comes to large scale clusters, right? There essentially is no competitor. So even our competitors would use Apache Spark, but it's something that we develop and we run. So Apache Spark is essentially a unified computing engine, and it's a set of libraries to do parallel processing in computer clusters. So Spark today is the most actively developed open source engine for this task. And it's now it's actually the de facto standards when it comes to large scale data. We support a variety of languages, Python, Java, Scala, and R. And there's also a diverse set of libraries that allows you to do machine learning on it. If you're familiar with Pandas data frames, Spark data frames are similar. You can also now use Pandas data frames, with huge data sets, and just put it through a Spark engine to do the compute. From a basic architecture point of view, it looks like this, right? So Spark applications consist of a driver process and a set of executor process. So think of this as your GPUs or your CPUs doing your compute. The driver process actually runs your main function. So if you've used MPI, back in the day, in the 1990s, I used to use PVM on supercomputers, right? You would have like a main function that would distribute the task. Today, through Spark, the distribution is largely automatic. Memory management is automatic. So the driver process runs your main function. It sits on a node in the cluster and is responsible for three things. Firstly, it's responsible for maintaining information about the Spark application that you've written. Secondly, it responds to any user's program or input, right? And thirdly, it's used to analyze, distribute, and schedule work across the executors. So it's sort of like a master kind of process that manages the executors. Now, the executors are responsible for actually executing the work that you give it. And that's all assigned by the driver. So this means that each of the executors is only responsible for two things: executing code assigned to it by the driver, and reporting the state of computation on the executor back to the driver node. And that's essentially the Spark architecture in a nutshell, right? It's far more complicated if you look at the code, but that's the top line of it. How would you access Spark? You would access it through an API. And here's a quick overview of the modules within Spark, right? You've got Spark SQL data frames, similar to Panda data frames, but it's meant for big data. It's meant for terabytes, petabytes, exabytes of data. Unlike a normal data frame, you can do streaming on it. And this is a huge enabler for manufacturing, where you get streaming data coming in from IoT sources, you get streaming data coming in from external sources, things like, if you are building a whole supply chain pipeline from pricing, freight pricing, to weather conditions and things like that, which you can't normally do within a pandas data frame. And then we've got a mlib for machine learning, right? So a distributed machine learning library that other libraries can sit over. At the heart of it is a Spark Core API, and we support languages like R, SQL, Python, Scala, and Java. The most preferred language, of course, is Python. R is interesting, right? Because many people will tell you that you cannot take R into production. You can with this architecture, right? You can actually put R into production with this architecture, which is a huge. But how does it look like in code? And I know many of you write code. I still do write code. I love writing code. How do you do machine learning at scale? And this is just a quick snapshot on how this looks like. So let's say you've got a TensorFlow code here, and you define a training function with a learning rate of 0.1, right? So you get your data set, you get your model, you specify what your optimizer is, eta, delta, you compile the model, you fit it, and then you train it, right? Sorry, this should be indented slightly to the left, right? Train is outside the defined function. So that's how you train the model, right? In a nutshell. How does it look like when you want to use Spark? So in Spark, there are two parts. One of it is that you need to distribute the data over the cluster. And we use a technology called Petastorm. So I'm not showing you Petastorm here, but the data needs to be distributed across the cluster by the driver to the executors. The second thing is the training of the module. So in a nutshell, this is it. So we've got something called a Horoward runner that sits over Uber's Horoward. So here you specify the TensorFlow, you import the TensorFlow Keras module from Horoward. You initialize the Horoward module, and all you do is what you did for a single node. And this is how you execute it. You're running it on 2 executors, right? With a specific learning rate. And the efficiency of this comes when you are doing things like hyperparameter tuning, right? So you do hyperparameter tuning like the way that you would normally do it, but you do it over a cluster so that you do it quicker. And this is extremely critical in industry, because in industry, you're running hundreds of thousands of models a day. And if you don't have a supercomputer in-house, the only way to do it is in the cloud. In the cloud, it's much better to do it in the cloud because it's scalable. You're not paying for time when you're not using the pieces of equipment. In the cloud, you're only paying for when you're training the model. You're not paying when you're not running the model. Well, if you invest in a piece of hardware, there are many companies that I've worked for which have got an in-house supercomputer. That is a capital investment. In order to maximize that capital investment, you need to be running models all the time. Now, there's an even easier way of distributing a model. And in recent times, we've introduced this apply in pandas functions. And for simpler non-deep learning problems, this is the way to do it. Let's say that you're optimizing a time series model like Nixla or one of the ARIMA models or things like that. Now, the function that you write is this build, tune, and score models. Now, let's say now that you've got a pandas data frame, right, with multiple columns of data. In order to distribute the problems over multiple CPUs or GPUs, all you need to do is to group the data by how many groups you want it to group by. So you're grouping it by group 1 and group 2 and dividing it by those groups, and then just calling this apply in pandas, right? Build, tune, score model, and then using a tuning schema. And that would automatically distribute your model in the cloud, in a Spark architecture. So it's becoming that easy to use Spark. In fact, it's that easy to use Spark. And how our users using this? If you look at computer vision, for example, and this is if you go and Google for a blog post with computer vision, and if you stick my name in it, you should find this article where we've got edge devices. These are cameras. In this case, we've used Raspberry Pi devices, feeding data using a technology called autoloader from Databricks to actually load the data into storage, right, into Delta Lake, right? Along the way, we do things. We have a medallion architecture to refine the data and put it into storage. Delta Lake being a lake architecture, allows you to store it as tables, but also allows you to store images and things like that. And then what you do is you train your model. In this case, we're using PyTorch to train a mobile VNet version 3, right? So distributing the problem. So we are using Petastorm here to distribute the data into for the executors, and then using Horowat to go and train the data, right? Now, the next step is how do you deploy the trained models? Well, once you've got a matrix to go and measure the accuracy of models, how do you deploy it? And the way to deploy it is MLflow, right? And MLflow is another one of our biggest open source projects, right? It's our second or third biggest open source projects. You can either deploy it as a REST API, as a microservice. So within the Databricks, our commercial environment, through about 4 or 5 clicks, you can actually go and deploy a machine learning model. So you don't need a whole software engineering team to go and deploy the model. Huge game changer there, right? Or if you need to deploy the model on the device, you can also do so. You can either pickle the model, you know, in Pandas, you can in Java, I'm sorry, in Python, you can actually pickle the model, or you can use you know, one of the standard protocols to shift the model onto the edge device and score the models onto the edge device. So this is an example where some of our customers are using it on the edge device. Next, it comes to streaming, right?
Dr. Bala, just to reminder, we have a few minutes and we can have US session as well. So if you kindly,
sure. Okay, thank you. Thank you for the time check. I'll wrap it up in 3 minutes, right? I mentioned streaming is extremely important. As I mentioned, you can do streaming because you want to do analytics over streaming, right? You want to be able to do performance measures, which is in real time over streaming. And that enables us to build architectures like this. Architectures where data is consumed from edge devices and fed back to edge devices. You know, things like this. When you're talking about edge devices like machines on the ground, you're not talking about HTTP protocols anymore. You're talking about MQTT, Kafka. You're talking about things like OPC UA and protocols like that. So we can build this to stream these protocols into Delta and then do data science workloads on it. Very quickly, two of our biggest customers in manufacturing, one of it is Shell, running over 200,000 models a day, every day, 250 engineers collaborating on the platform, 70 over use cases from supply chain to operations to looking at the failure of valves, valves when it comes to oil and gas, looking at predicting the failure of it. The outcome of this is the ones on the right? Well, one of it is CO2 reductions, huge CO2 reductions. The second use case, and I encourage you to look out for a video of this. It's actually online if you look for the video on it. The CIO of Rolls-Royce jet engines is a huge proponent of Databricks and Spark. And they use Databricks to do predictive maintenance and digital twins over 13,500 jet engines. And it's all flowing onto our platform. And you can see the impact of doing that, right? All the data is flowing to the Lakehouse architecture. All the analytics is being performed using Spark on the Databricks platform. I'll wrap up by saying, right, we do write a lot. As I said, we are hugely open source, open standards. We like sharing. And if you go onto our website, databricks.com/blogs, you'll find all kinds of things, a lot of source code that we release. One that I've just co-written with some of my colleagues in Databricks is how to do fine-grained time series forecasting at scale, right? So how do you distribute a task? And so that you can run millions of models a day. So some of our biggest customers, we have one customer in the US running 7 million models a day. And how do you do it at scale in a cost-effective manner? So I'd ask you to look out for that. So that brings me to the end of my talk. It leaves us with about 7 minutes. So I hope that you can cover your questions.
Thank you. Thank you very much indeed. Wonderful presentation and so many special industrial things. So any questions? Because we have only a few minutes. So one short question from anyone. Okay, if not, I have a question. We discussed about the IoT devices. Now, edge devices are extremely rapid. Rapidly changing, and we have new devices. The point is that when we consider the tiny ML, do you have the tiny ML incorporation in your system?
Yes. We do actually have a third party. In fact, I can't pre-announce a partnership, right? But we do actually have a third party connector, which is coming out within, I would believe, in the next month or two. that will allow you to consume directly through an MQTT broker. So at the moment, the path to doing it there is that you have an MQTT broker that absorbs data from TinyML. You shift it to an intermediary device, which is in the cloud, on, let's say, Azure IoT Hub, or if you're using AWS, AWS Sidewise, Greengrass, and so on. And then you do the conversion to Delta. What we have is a new partnership. It's actually an open source partnership, just because of a huge fan of being open source, where you can have your TinyML device talking directly to an MQTT broker in the cloud, and then shifting data, so there wouldn't be a conversion straight to Delta. So yes, it's doable today. It's going to be easier in a month or two time.
All right, well, excellent. So there are more issues, especially from my side, especially when you discuss about the vision and the IoT sensors and others.
Yes.
I will talk to you offline in the near future, because now I'm in university, so it would be wonderful to talk.
Yes.
Thank you very much, and I request the organizer to share the just a certificate as just a good gesture. So, Dr. Bala, we are grateful for your time and wonderful presentations. Thank you so much.
Okay. Thanks so much for having me here. It's been wonderful just interacting with all of you.
Hello. Hello, can you hear me?
Yes, you can. Yes.
Thank you all for joining with us, and thanks, Mr. Professor Dr. Bala Ambashi, for sharing his speech with us. And we are delighted to share you that we have a certificate for you, and we are going to share it in our screen.
So Bala, you need to unshare your screen, I think.
Let me just stop the share.
Yeah.
Oh, so Dr. Bala Ambashi, if you look on his screen, this is a certificate for you.
Okay, thanks so much. Really appreciate it.
You're most welcome. Thank you all. Gentlemen, we have to move forward in our next keynote session. We are always grateful to yours for your precious time. Thank you all.
Thank you very much.
Yeah. Thank you, Bala. Thank you.
Thanks a lot for having me. Really appreciate it.
Yeah. So, gentlemen, we are now moving for our keynote session 9, which will be conducted by Professor Petrolio. And for this session, we have our session chair, Professor Dr. A.B.M. Shaukat Ali, CQ University, Australia. And we have our session moderator, MD Shahriar Shetu, NSTU Bangladesh. And conducting this part of the session, I am requesting session moderator, MD Shahriar Shetu, come forward and conduct the rest of the session. Thank you all.
So just instruct me if I need to start again. I mean now.
Yes, sir, I'm hearing you.
So I'm waiting for your signal. Should I start?
First, I want to introduce Professor.
Right. Okay, sure.
Yes. I will introduce Professor Petrolio. Dr. Petrolio is a full professor at the Department of Computer Science and Technology of the University of Cambridge. He is a member of Artificial Intelligence Group. He is also a member of Cambridge Center for AI in Medicine Steering Committee, member of Cambridge Big Data, member of BPH UK, Virtual Psychological Physiological Human Fellow, and member of Counseling of Clare Hall College, a member of Mark Foundation Integrate Cancer Medicine Institute, member of European Lab for Learning and Intelligent System, ELLIS, and member of Academic Europea. Dr. Petro received a MA from Cambridge, a PhD in complex system and nonlinear dynamics, and another PhD in theoretical genetics. His research interests focus on developing artificial intelligence and computational biology model to understand disease complexity and address personalized and precision medicine. Current focus is on graphics neural network modeling. Publication: he is published over 600 publications and received
33,000 citations. His Google Scholar HI index is 63 and I-10 index is 264. He is awarded many grants, and current grants are included Mark Foundation, European Horizon 2022, and NIC GSK, AstraZeneca, SRC, Armstrong. He has completed supervision over 23 PhD students, 32 MPhil students, and currently supervising 60 PhD students. Now I am requesting Professor ABM Shaukat Ali to conduct this session as a session chair. Thank you.
Okay.
Good
Thank you,
afternoon.
Situ.
Yes, sir.
Good afternoon.
Yep. Thank you. Okay. Colleagues and audience, good evening from my side. Good afternoon from Bangladesh. And the rest of the people, I believe, I should say good morning. So it's my pleasure and honor for me as well, to do chairing very well-known professor from University of Cambridge in this session. So you may see, audience, Setu already introduced our keynote speaker. So, as an academic, I feel, some title, one title is enough if somebody is professor. However, it doesn't work in research. In research, we measure the number with H index. So you can see what is H index Professor Liu has. So I'm not going that way. So you can, listen his talk, and then after that, you guys will realize, what is it. However, briefly, I would like to tell his topic here, building multimodality digital patient twin using graph neural networks. I believe audience is very keen to know and learn our keynote speaker rather than I read his abstract. So without any delay, I would like to request our keynote speaker, Professor Petru. You may start, sir, and please allow few minutes at the end of your talk to the audience if they have any question to ask you. Thank you, Professor. Please. Now, floor is yours. All the best.
Very well. Thank you. And first of all, I apologize not to be with you in Bangladesh. The health situation condition of my mother, who is now hospitalized and was something expected, was something that refrained me from traveling too much in this period. I would like to start with this image, which is my department, because it's also the department where Professor Mohammed Moni, my best PhD student, was trained. And so we because we are sharing this, that is how I would like to start. This is a department also where the first practical storage programming electronic computer was built, the DSAC. And even if you can imagine that is something that is nowadays less convenient than the computation that we can do with a mobile phone. But that is how, in some sense, the field has progressed, and we should be very happy of what we have achieved. Now, the agenda. I have a lot of slides, so on some of them I will go quickly. Particularly, I put some introduction material just for any students in the audience, but I will be quick on that in order not to annoy the most senior colleagues. So I will say something about graph representation learning, how to improve the performances of the current architectures, and also how this could be deployed in medicine at different levels, particularly bench side and bedside. So in the lab activity to discover and to design medicines, but also at the bedside to administer this medicine to the patient. And then I would say about the digital patient. First of all, we are very much accustomed to the convolutional neural networks, where in some sense we need the large data sets and also inductive biases. Particularly the fact is that together with a pixel, we consider all the local receptive fields made by the surrounding pixel. And this has led to a lot of research on the convolution on images. But I think equally interesting is coming to see the data, even the image has graphs. And this, it brings also a shift from an Euclidean point of view to a non-Euclidean point of view, which also is interesting from an information perspective, because we can transform pixel on a regular grid on superpixel. And the graphs are everywhere. Even each image that you see in this slide is a graph, but they can also be seen as a single graph with our imagination and our thinking of finding relationship. Even the way that we do research nowadays is a graph. And this is something that is very different from the time of almost isolated scientists like Galileo. Now I think that we can hold conferences, big conferences like this, or research groups with people who are in some sense localized geographically in different places. And even, for instance, our manufacturing or our biology can be seen as a graph. Obviously, the biology is not only made by graph, but is also encoding the dynamics, the building up, the self-assembling of graph in the memory. And that is probably why biology is considered the next machine learning. In terms of formulation, and I will be very, very quick, a graph is a collection of object interactions. And what is we want to see is the adjacency matrix from which we can derive a Laplacian, because the adjacency matrix contains all the information that we need to proceed in our analysis of a graph. And there are different graph types: undirected, weighted, multi-relational, heterogeneous. We can look at graphs by scale. For instance, we can concentrate on the node level, on the edge levels, on the graph levels, with different kind of interpretation that we do. But we can also see at graphs from a domain point of view. For instance, we can do training of a neural network seeing all the nodes, or instead the test nodes remaining unseen. So the most important task that we need to address is to do node embeddings. And this means that the original network will go in a space that is the embedding space. But how to do that? Well, we want to do that finding an encoder that will allow to then extract the information with all the features, but also the neighborhood of the node that we are targeting. So in some sense, we want to do in order to preserve the graph structure. And this is at the core of the graph neural network. Particularly, we need to find ways to aggregate informations from the nearest neighbors and also from the other nodes as well, and to transfer data to the embedded space. And this is what is happening in a graph neural network. And this leads to different kind of output. We can do node classification, for instance. We can do graph classification, and we can do link prediction. The link prediction could be useful, for instance, for finding trajectories in a graph. The node classification could be good, for instance, to assign a node to, for instance, if we are talking of people with disease, with a healthy or patient. Or graph classification could lead, for instance, to identify a subclass of disease. This means that we can build layers that are connected by nonlinear functions, no? Because the deep learning at the end relies in the fact that the layers are built are connected by nonlinearity, and this allows us to detect the nonlinear patterns in nature, which is in some sense the fundamental aspect of our world. So this is the sort of setting of graph neural networks, and till now, in a rapidly growing field, we can find at least 3 flavors: the convolutional graph neural networks, the attentional graph neural networks, and the message passing graph neural networks. They are quite recent, all of them anyway. Probably the convolutional, the sort of the oldest, but it's something that we talk of 2016. And in this case, we have fixed weights between the nearest neighbor nodes. So the aggregation allows also quite a lot of property of scalability. In the attentional graph neural networks, we look instead for implicit weights that could be through regression or correlation. And that is in some sense something that is leading to a lot of interesting properties that are particularly relevant in a new class of architectures, which are the transformers, both the standard transformers and the vision transformers. So the standard transformers were born for natural language processing, and the vision transformer, they can do, analyze image and videos. They have the attention as the core, and actually now the attention could be not only like a regression setting, but could be also a spectral function like Fourier or wavelets, which brings interesting aspect in terms of using graph neural network for signal processing. And then we have a message passing GNN, where these are very powerful, more difficult to handle in some sense, also, but very powerful because they can have messages that could change in time, and that brings the possibility also to link to other kind of methodologies, like even Bayesian approach and so on. There is, and this is for the students, could be a good news, a rich ecosystem of libraries, because they can go on the line of PyTorch, and we have PyTorch, geometric PyTorch, or DGL, or one of my students has developed this PyTorch geometrical temporal. Or they can go on the line of TensorFlow, so that we have TensorFlow graph neural networks, or Spectrum, or on this new kind of new library from DeepMind, the JAX, and this incorporates more mathematical capability, and this has also a giraffe and has a graph neural network dedicated library. There are also benchmarks that have been built for the purpose of the graph neural networks. I will go quickly on this, but I need to tell you also the troubles. No, we have also some problems in using the graph neural networks, and there are some partial solutions that I will just mention about using directional Schiff, hypergraph, or Ricci curvature approach. The two problems that are very much related are the over-squashing, the inability for graph neural network to propagate signals between distant nodes. And this is something that is more general to the deep learning, actually. And the over-smoothing. So the node representation becomes is degraded when there are a lot of layers. And now this is an hot area with a lot of people proposing solutions. I've been working, for instance, on the fact that these problems could be ameliorated when you have systems that have some directionality. In this case, having some directionality, you can try to aggregate nodes that are following that directionality. So instead of the asymmetric aggregation, you take into account of the system under study, and you can, for instance, develop a method based on eigenvectors that will find the most optimal directions to make the aggregation. And this, I will skip the details. Getting the aggregation and getting the derivative of this aggregation is leading to a lot of improvement in the performance and in ameliorating these problems. So that is the directional GNN has much lower errors than other commonly used networks. Another approach is instead to overload the graph neural networks and add on the nodes and edges some vectorial fields. So these vectors fields can contain information that could also be related to a different granularity or a subgraph structure of the GNN. And this is a very new direction that was stemmed by some mathematical papers. And we are, I cannot tell you of any kind of important applications because the theory is being deployed. So the Schiff neural networks. Another approach to ameliorate this is instead to look for higher order networks. So instead of having graph neural networks, to have hypergraph neural networks or simplicial complex neural networks. What we gain? Well, the main point is that in the graph neural network, the interaction that we consider is always between a pair of nodes, okay? So we build everything from a pair of node interactions. But in many physical, chemical, biological systems, actually, there is a multiple interaction, a multi-node interaction. This is why hypergraphs and also simplicial complex, which are in some sense more constrained than the hypergraph, but mathematically more interesting from a formalization and so on. The hypergraphs seems quite an optimal solution that also could lead to ameliorate the problems that I was mentioning before. Something that is actively researched is also the fact to understand from a graph point of view a property that is used in differential geometry. In differential geometry, the Ricci curvature that has been used in general relativity, but also in the work from Perelman and others, it looks like that is telling us how a graph is deformed or is changed. And so using this analogy between the differential geometry and the graph, we are able to bring the Ricci curvature into this. And that is something that is showing that could also help with the oversmoothing and oversquashing. This is the Ricci flow in general is coming from a tensor equation that tells us how a certain shape with a particular volumes will evolve in time, so that we can understand how the curvature of that is in the GNN will change with the optimization of that is brought by the working of a network. Another approach that we are using is it goes in the direction of not only of addressing the oversmoothing, oversquashing, but also to make the deep learning more interpretable and explainable. Okay? This is very important because any deployability, actionability in a hospital or in any other aspect of our society will bring liability. And that means that we have to respond of any output that has is bringing consequences to the life and the well-being of a person. So we are trying to put together aspects that are going to the attention that I was mentioning before, with aspect of a concept. So the fact that when we are using a neural network, we want that the neural network will extract and will make suggestions that are online with what our expert will do. So if it's an expert an expert doctor that will diagnose the rheumatoid arthritis, for instance, one of the main features is how narrow are the bones. And this is something, for instance, that we want also the neural network to take into account, and not just to use some naive approach. This is why the concept, how a concept, like for instance, this narrowing of the bones, is in the neural network, how it's coded by an ensemble of nodes, is very important. The same, an example here is to recognize a bird species from the wing and so on, and the logic itself. So using concept, attention, and logic, putting together these three elements, we are some sort of achieving some interesting results into explainability. And that, in some sense, in my opinion, is something that will also turn into even improving the architecture itself, not only making more explainable, but even better, so that we are able to explain to a doctor why what we are building is suggesting a certain drug or a certain diagnosis. This is something that we are working now. We have built this logic explainer network device that is we can plug to any deep learning. We are also using that for the graph neural network approach. So that is, in my opinion, something that will make possible to have a machine learning person that is able to communicate and to discuss in a forum of doctors in a way that will be really constructive. Let's get into a bit more AI and medicine. Is a tremendously vast field that goes from the molecules to the device. I think Professor Mohammed Moni has given a very effective introduction and illustration of the devices that could improve the life of a patient. Let me so focus a bit more on the bench side. So, for instance, at a molecular scale, it is possible nowadays to use the graph neural network for generative purposes. For instance, if there is a protein that is overexpressed, and is a protein that could contribute to inflammatory progression or to cancer, we are able to design a molecule that could fit a pocket, even if the protein has a dynamic, we can find the best way to get a drug that could be trapped in that volume. This could be achieved, for instance, with some software that we have developed, graphene, and we have also used that to try to design antibodies. So when there is a new viral infection, we are hurrying up to get the genomic of the genomic structure of the virus, and then to design some drugs. This is something, in my opinion, that AI will play a fantastic role, so that we can design the antibody and we can inject the antibodies in the patient in a very short time after we sequence the genome. That would make a much rapid reactivity than what we have seen with SARS-CoV-2. Something that we have done recently is to take into account that we are getting a lot of data from different organs, and these and single cells in particular. So there is a project, a large international project on tissue gene expression, and there will be tissue methylation, but there is also an atlas of single cell. So we thought that the scarce capacity of GNN to deal with multi-interaction could be overpassed by the use of hypergraph neural networks. So we have recently developed, and is a paper that we put in bioRxiv in August, an hypergraph factorization, where we are able to analyze simultaneously many tissues and single cells. And this has led us also on to develop an imputation method, so a way that we can even generate data. And that is very important, because is very difficult nowadays to share data because of the privacy. So one of the most important aspects of deep learning is the capability to capture the multi-factorial distributions and to generate data according to those distributions. This I will skip because in some sense it is something that you can see in the paper, but this leads also to understand the similarities between tissues, and also the fact how, for instance, regulatory circuits may be in place that could explain that similarities. But I will skip. So we found something interesting, for instance, between the gastrointestinal tissues and some tissue in the central nervous systems and so on. But this is a lot of details that it will take time to tell you about. But I wanted just to show that this is, in my opinion, nowadays possible with good accuracy. Now, at a cellular scale, let me show one example, and then another in few minutes. The most interesting aspect that I've been using graph neural network is the fact that in many tissues of our body are very regular patterns of cells. So if you look, for instance, at the liver or the epithelia, the cells are very regular. And this is very important because we can extract a metric so that the lack of regularity is what happens when there are, for instance, inflammatory or cancer dynamics. The cancer, because the cells are starting dividing in very rapidly, they break the regularity of the pattern. So that if you extract a tissue, a biopsy, and then you look at the biopsy with new eyes, not like an image that you would use with a convolution, but you use as a graph, then you can input that in a graph neural network. And that brings you a lot of information about, for instance, how much the percolation of disruption of regularity has gone, and what are, if there are preferential direction for this percolation of disruption, and if, for instance, is multi-clonal or is single clonal, which is very important because a multi-clonal cancer is more difficult to handle, because it could be that a certain treatment could stop and kill the cell in a clone, but not perhaps a nearby clone that has a different mutation. So this is something that, in my opinion, could be implemented as a tool in medicine. And let me now introduce how we can bring the information that I showed till now into a more systemic way. So first of all, something that I really like in deep learning is that it becomes a new way to do modeling. You can do modeling using analytic, so using, for instance, differential equations and or partial differential equation or other methods. You can do modeling using cellular automata or other computational methods, but you can also solve differential equation or PDE using neural networks. And this is very interesting because it brings also a new mentality in doing this. Obviously, there are problems that has been solved only partially, like, for instance, the fact that the back propagation needs, for instance, to be used with an adjoint method for ODE solver. But this is something that also, what is interesting is that if you look, for instance, at a residual network like a ResNet or something, this is, you see the architecture, you see that is immediately has the shape of solving an ODE with a Euler approach, because you have different layers, and each layer represents, for instance, two different time instances. So that is what you want, to compute the Euler system. But also graph neural networks can be very useful for that, because in this case, the graph could be both a geographical graph, like your body. For instance, you are taking signals at the periphery, and you are using those signals to predict, for instance, the state of your heart. Or the graph is made by the parameters in each equations. So what is happening is that using this approach of neural ODE, particularly with a graph, you can put together information both spatially, but also by the scale, the biological scale, so that you can put together the aspect of gene expression with something that is happening at the level of physiology, like, for instance, the different signals that goes through that go through the motorways that are our vein and arteries. Okay, and this is something that we have built in a modular way. And this is a digital patient that is a sort of avatar of a patient, so that the patient could have something to compare with, so that also to realize what is happening, but also something that it could be also receiving signals from sensors, body sensors or intra-body sensors, and that is important because the possibility of linking together different parts of the body, also different scales of biology, makes possible to understand better a systemic medicine. How, for instance, we have a long-range correlation in our body that are affecting and are causing, for instance, comorbidities. I will skip part of the architecture because we have published one paper and another is coming, and this is a GNN that is linked to a generative adversarial network. And this is very important because it allows to develop also a system for synthetic data. And these synthetic data are, in my opinion, something that will help also share protocols, but also share material from big hospitals to small hospitals in the countryside. So we can do democratization of some aspect of medicine. And we can get, and we can put together different aspects from different parts of the body, so we can have a better view of the patient. This allows also to understand and to have a sort of what if. What if a patient is able to change lifestyle? What is happening if a patient, for instance, undergoes to this surgery or not? Okay, so this is something that we are sort of very interested in building up, and this is some aspect, for instance, of the generating data, for instance, understanding the difference between cancer and non-cancer. I will skip this. Something that we are doing, and it goes between the cellular and the body, is also we are doing something on the immune system. The immune system is very large, but it's so important because is really our defense, but it crosstalks with all the organs, okay? And it's very, very, is 1 kilogram of cells that are moving in our body, making a lot of signaling. So signaling is the real point of this the immune system, which is modular because there is an innate and an adaptive immune system, but also is part of inflammation. And also, more important and more interesting, is at the core nowadays of our research in cancer. We think that knowing better the immune system, we can address and we can derive better solution for cancer. It's what is called oncoimmunology. I will skip this. I want to go to the next level and say something also what is happening when for doctors. Okay, so can I use all this information from the digital twin to really have something good deployed in medicine? The answer, in my opinion, is yes. First of all, we tried with the intensive care unit data because, in my opinion, this is what is the real point of having a method that is able to give suggestions very quickly. Because when a patient arrives in intensive care, in emergency yard, doctors have to be well trained to try something the best immediately. And this is something that we look for a database, which is very, very big, contains a lot of types of data. So we exemplify on the method on the diagnosis. And each patient becomes a sort of fingerprints of information, okay? The information are about all the events that happen to this patient in his or her life, okay? The fact that at a certain time got the diabetes or got a fall, made some trauma, and so on. So you have all this information that is like a fingerprint, and that is something that you can digest through a network. Obviously, there are common diseases and rare diseases. So if you have to check how unbalanced are the data, okay? Because there are some diseases that are happening only on a small number of patients, while for others there is much more statistics, and that is something that is a problem that has to be addressed. But what is important is to conceptualize this approach. So if, for instance, you are a doctor and you have a new patient, there is a ring at the door, a person enters and say, doctors, I have this problem. What you do as a doctor? The most important thing is that if you are a doctor that has a lot of experience, you should recollect immediately some other past patients, if they were with similar symptoms, so that you can, in some sense, bring that past experience into work now. This is what we have done. In some sense, the kind of network of patients becomes a network of nodes. And if you have a network of nodes, I am the person that will make a graph neural network, okay? So in some sense, from this conceptualization from a doctor, you get an architecture conceptualization. And obviously, you have to, for instance, to take into account that you want two patients to be at a close distance each other, depending how many features they are sharing with respect to the totality of the feature, okay? And this is the formula that you see here, is that how many common diagnoses, how many common features they share with respect to the diagnosis that each of them got. This is a sort of normalization approach. And after that, you can construct the graph, and then you can do the embedding of this graph, and you can run. This is just some results, but is very partial. But you can predict the length to stay in a hospital, which is something that also is important for the patient, but is important also for from economic point of view, and also the mortality results. And all the GNN were very, very good, or at least better than other currently proposed methods in addressing that. Obviously, the more graph-like is your problem, the more likely a graph neural network will be good or good enough to provide some solution, okay? And then with the attention, you can, and I have only 2 or 3 minutes, I think, with the attention, you have, you have the possibility of understanding also what was important in the fingerprint that has led to that kind of diagnosis, okay? That is, we are building this into a much sort of pipeline, a much comprehensive pipeline that we call VIDA, is visual integrating interactive data. And this includes logic aspects. And the idea is to help deciding things. If a patient has to be given an existing therapy or an experimental therapy, or perhaps don't treat. And also, in some sense, this goes into what we think is the landscape of what we see AI nowadays. And the last slide is that putting my research in the future will be more and more on putting the information from different scales all together in order to have diagnoses that are more effective and optimal for the life. Thank you very much.
Thanks, Professor Petro. We are honored you have given your precious time for us. And we, the student of Noakhali Science and Technology University, believe that we learn a lot of things from you. And we hope you will contact with us, you will respond with us in future too. We are very hopeful and very optimistic about these issues. Thank you for Petro. Now I am giving the floor to the session chairs for running the Q&A session.
Okay, thank you, MC. Thank you, Professor Petro. Wonderful talk, wonderful talk. I was looking at the graphics and your solution, just impressed. Yep. Since we are running out of time, maybe we can take a few questions. So first I can see hands on, Professor Atik. Yeah, please move forward.
Yes, thank you very much. Thank you, Pietro, for your excellent presentation indeed. So you raised various issues, but I can't ask everything now. I have one question regarding the forecasting or predicting, where in a paper, that towards the digital twin regarding patients' medical conditions. So in that paper, when I read it, you have basically two different real patient cases, and you collected data from that. So that's challenging. And of course, based on two patients, it's also very difficult to predict and forecast about the, genuine forecast and possibilities. So how do you feel about that? Because I have been working on remote similar concept, like remote patient monitoring systems with stroke patients, Parkinson's disease, Alzheimer's disease, and to predict. And when we collected data from them, like different kinds of sensor-based data or other data, and from hospital for ground truth, we find it that it's very difficult and diversity is huge. So, huge diversity based on the level of patients and so on. So the reality is extremely difficult. Just please give us some more about this and how I can or we can just move further regarding this kind of things. Thank you.
So I agree completely. This is why my research is to put together data-driven learning, but also physically inspired learning. So in some sense, equations. There are so many important models in physiology that has been validated with patients. So in some sense, putting together, for instance, I used a set of about 50 differential equations to model the cardiovascular system. And this has been proposed in the past and validated, and I made only little change to that and so on. So I'm using a sort of integration of equation-based modeling, which is knowledge that has been validated with data-driven, and the data-driven are very much partial. For instance, it's very difficult to find immune system data for so many of these cell types and so on. But at this point, the digital twin becomes also a scaffold where you can put these things in the right position and try how they dialogue between them. The it is a partial solution, but is the best that we can do now. And it is good just to get the next step, and also to be able, for instance, to extract information from very cheap peripheral measures, like, for instance, blood pressure, oxygen levels, and so on, that are very cheap, and infer from these cheap peripheral measures something that is happening at the level of the central, for instance, where in some methods have to be more invasive.
Thank you very much. We'll discuss more in the future. So
Yes.
thank you.
Yes, very,
Thank
very.
you. Okay. Yeah, I can see, Professor, your student is here now in the queue to ask the question. Yep.
He's not
Mohammed
anymore
Moni,
my
please.
student. He's not anymore my student. He's a colleague, and actually he's an important colleague nowadays. So because just a quick comment, you judge your career not only from the papers, but from how many students have become professors and internationally recognized scientists. So in some sense, Professor Moni now is actually enriching my portfolio, because I can say that I have trained an important professor.
Thank you, sir. Thank you, sir. Yep. I have
but
some
actually-
what Mani, if you give me 1 minute, I have some similarity with you with Mohammed Mani. So I had the opportunity to teach him in the undergrad level. So you taught him in the postgrad level. So we
Yes.
are in the same boat, sir. Yep.
Yes,
Thank you.
So, actually, ABM Shaukatali, Professor ABM Shaukatali sir is my undergraduate teacher, a classroom teacher. So I'm
My
privileged
pleasure, my
that
pleasure.
both of you are now today. So actually, I did not want to ask any question to Professor Pietro Dio. I wanted to discuss something with Professor Atikur Rahman Ahad Bhai, because I am doing the similar things and I'm facing the similar problem that he is facing, and we got some solution that we can do. But if we have limited time, we can avoid now. We can discuss later. Otherwise, I can tell something.
Hello. Hello,
Yeah,
sir.
we can discuss later because we don't have time today.
Yeah,
Yes,
that is
thank
the
you.
point.
Thank
Maybe
you.
we can discuss later.
Hello, sir.
Okay.
Hello, sir.
Yes.
This is from the
Yes.
session coordinator. Sir, we are running out of time. We have another session in 5:50. So, sir, we have another session 4:30, sir.
All right.
Okay.
So I think I need to close the thing.
Yeah.
Okay. No, thank you. I had few questions as well. Talk is very interesting, especially digital twin is my interest too. Anyway, we'll discuss later on. So
Yes.
on behalf of the conference organizing team and audience, I would like to say thank you, Professor Pietro. It's an honor for us. You are with us nearly 1 hour.
Thank
I
you,
know,
sir.
It's an honor also
I
for
know,
me.
Share-
one single minute is valuable for you. So you spend a long time for us. Thank you again, sir.
We have
Yes,
another
please.
thing to share for you for Professor Petro. Sir, we the organizing team have arranged a certificate for Professor Petro. You can see it in your screen.
Yes, thank you. It's an honor for me. It's unfortunate that I have this health issue with my mother, but otherwise I hope to visit you at a certain point, because it will be a big honor and a pleasure.
So I request organizer, please send this certificate by email. And Professor Petro, from our end, our every prayer will remember your mother. God will take care of your mother.
Thank you very
Thank
much.
you, Professor Petro. God bless you. Thank you.
Thank you, and thank you very much.
Bye-bye.
Thank you, sir. Sir, certificate will be mailed by the organizer, and it will be done by Shahriar Setu, sir, from NSQ Bangladesh. Thank you, sir. Sir, we have another session, Keynote 10, Keynote session 10.
Hello, everyone. This is Prashant Dev. So now we are starting our Keynote session 10, session title, Human Genome Research in BCSIR Bangladesh in context of SARS-CoV-2. This session will be conducted by Dr. M. Samiruzzaman, co-founder and chairman, SciTech Consulting and Solutions. Our honorable session chairs are Dr. Mohammad Ali Moni from Australia and Professor Dr. M.D. Shamsul Arifin, Chuet, Bangladesh. Our honorable session moderator is Kamruজ্জামান from NSU, Bangladesh. Now I would like to invite our honorable session moderator to conduct this session.
Thank you, everybody. Welcome to our international conference on machine intelligence and emerging technology. Now I would like to request to conduct the session to our session chair, Professor Dr. Shamsul Arifin sir and Muhammad Ali Moni sir. Sir, please conduct the session.
Maybe I can conduct the session if like Shamsul Arifin by busy. So would you like to share your slide, Dr. Samir?
Can you hear me first of all?
Yeah.
Yes, we can.
So.
Oh, brilliant. Yeah.
So would you like to introduce him like Dr. Samir, or it is already done? Sharia.
Not yet.
Okay, so maybe I can introduce. Okay, I'm introducing Dr. M. Samiruজ্জামান. He is a visiting research associate at King's College London. He completed his bachelor degree in CSc Computer Science and Engineering from the BUET in 2003. And later he studied at postgraduate level at University of Oxford and completed his PhD from the King's College London. He has been working for UK government and different agencies in UK, including City of London corporations. He is a co-founder and chairman of Rokhi and SciTech in Bangladesh. He was the proposer and the principal consultant of the first human genome lab at BCSIR, Bangladesh. He is now the principal consultant of Next Generation Human Genome Center at NIB, Sabar. So Dr. Samir is now presenting an important issue, the current world pandemic, the COVID-19, and the genome from the coronavirus, like SARS-CoV-2. So there are different variants of SARS-CoV-2, but we would like to know the difference of the variants in Bangladesh with the other country, especially maybe the Wuhan in China. So we would like to know in different things related to the mutation of the genome sequence of COVID-19, like SARS-CoV-2, and how it is influencing in Bangladesh compared to the other countries. I request Dr. Samir to present his valuable talk related to the scenario of COVID-19 virus in Bangladesh. Thank you so much.
Thank you very much. Thank you for inviting me. Just first, I want to check that everyone can hear my voice clearly. Otherwise, I will adjust my sound here. Is it okay?
Okay, sir.
It's okay. Yeah.
Brilliant. So basically, I have today I looked at the audience of these seminars. Mainly, you guys are expert in various machine learning, data science related areas. So my title, I change a little bit so that I can interact through the audience properly. So I will talk about the genome studies as a multidisciplinary research and how the audience, especially from computer science, statistics, and mathematics, can get involved what Bangladesh is doing currently. So my talk will have two parts. One is the infrastructure and lab we have got in Bangladesh. And the second part, I will walk through, basically I came from computer science background, so I will walk through one of my algorithms, then the implementations, then how a simple algorithm from mathematical side can actually help the genomic community, especially in biological areas. So let's start my talk. So first one is we established a genome lab first genome lab in Bangladesh, BCSR in 2018. We started the process in 2017. We all know that we had Jute genome scientists who worked brilliant work in Bangladesh, but the facilities were not there. On that time, they used wet lab in Malaysia. So we felt as a researcher the necessity that Bangladesh should have the infrastructure so that a lot more other studies can be done, especially on human genome. Our main objective was think about our populations. We have roughly 180 million people. It's more than double than UK. In UK, there is like government, non-government. There's like thousands of labs. So we have the similar. We have bigger populations, but our genomic representations of data was very negligible. So we first thing we need to do as much sequencing as possible, and on different area we can work on identifying various biological problems. We have our own issues. I mean, Western world will do their best on the all known kind of disease, etc. So we have our own kind of disease and spectra, so that our drug should be different based on our human genome and what we have in our data. So that's very important that we have our data and we have a lot of researchers gets involved in this multidisciplinary research. It's a basic of, I just put a basic slide based on, I mean, if many of us came from computer science background in my audience. So if you think in data perspective, it's like a huge amount of data even in one person's human genome. If we can think about 3 billion letters, roughly 22,000 genes, and it is varied from various ethnicity to ethnicity. So like in South Africa, there is a group who has got 3,000 genes extra. We don't know yet. So it's a very initial stage to study human genomics properly. Again, in terms of data, so if we have 3 billion sequence and 1 in 1,000 base pairs, if we have the difference, that what makes us human different. I mean, we know that genome is the basic building block. It's a code. It produces, when it's expressed, it's produce RNA, it produce protein, and that actually makes us live as a human. So it's a biological process is quite complex. Mainly, I will talk about the data perspective, so that we know that where we can involve. The Human Genome Project, we know the evolution is if we start from 90s, and we ended up giving a complete code in 2003. And it costs like $13 billion, but nowadays the technology is in our hand. Just in a day, we can do hundreds of human genome data is within within our budget and very low cost. So I'm a bit sorry, this slide is a bit messy, so probably, yeah, move on. I'm giving you an idea, the kind of machineries we have in Bangladesh now. So in next generation sequencing, the latest machines the world has got now is Nova 6000. And we are lucky as to have one of these machines now in BCSIR lab, and it is extremely powerful. It has got 24 times 2, that means 48 human whole genome sample can be put together, and we can produce data within a day. So there are different kind of technologies exist in the world, and also there are now handheld technology came in the market. So probably that will change the game too. So mainly in Bangladesh now, Illumina sequencing is popular, and also worldwide they're the leaders. So they're doing very good in terms of NGS facilities. In BCSI lab, we have first 3 machines. Nova 6000 is a very high throughput whole genome sequencer. actually this is the best one. Then the second NextSeq 550 is also medium throughput. We have a minisec for the bacterial and viral genome, and we have other machineries like iScanner. We have the PCR machines and all the biological small machineries. So we, although we need lot of labs, but still we have one, and there is another one in making in NIB, and there are a few other non-government initiative as well. So hopefully soon there will be much bigger infrastructure than now. So why we felt the necessity to do the BCSR lab? On that time, if you look at the data, like when UK started 1,000 genome project, then 100,000, then 1 million. So basically, representation of our subcontinent's data was very, very poor. I mean, literally negligible. So we need to start producing our own data. That was the motivation behind the BCSR genome laboratory, and later on what government is now initiating, as well as the private sector. COVID-19 came suddenly. So when we started in 2018, our main target was doing the various local research. And also as a start, we started on breast cancer to finding out a biomarker. Like we know that BRCA1, BRCA2 is worldwide. We know that if it presents, so we can say that there's a possibility of having breast cancer in future. So in Bangladesh, breast cancer is a killer disease. So we started looking into the other way that if we can find a biomarker, we did some improvement. That work is on hold, and COVID-19 came up, and we had to put all our resources on getting all the variants tracking and giving the data to the vaccine companies, as well as making open data for the researchers so that we understand more about the Bangladeshi COVID situation. This is we took it in 2021. On that time, you see that BCSR itself, within very short period of time, just in G-site, we uploaded 760 viruses data. So not all of the data we published. The data we felt that vaccine companies and all the other researchers will be interested in, we put that in the public domain, and we were actually sending our findings to all the big vaccine candidate on that time when they were in the making, so that Bangladeshi human data is taken into consideration and vaccine works properly. As of like what will work for Western people, the same works for us, so that all the spike changes or whatever minor changes vaccine company feels important, we made the data available for them. So based on our communications with them, we can ensure that all the vaccine has been used in Bangladesh. Bangladeshi data has been taken into consideration, and BC has played a very important role on that time. So during COVID-19, all the genome sequencing has been done in Bangladesh, 76% done in BCSR lab, because they have the best facilities and they have worked hard around the clock. So this is a good infrastructure, and in future, a lot of collaborative work from various universities and research lab can be done. Now I will talk about 2 slides where a couple of good paper has been produced. If we have the data, so, and if we have got the analytical power, I mean, if we can have the analysis team, what we can do, this 2 slides is the example. So during COVID, we realized that not only COVID that actually affecting us is the co-infection during COVID. So we don't know why is that. Probably immunologist can say in one perspective, we as a data scientist sees in different way that we have seen data. So a lot of opportunistic bacteria and viruses affected us, and our sample size was quite considerable too. Like at first we started roughly with 100 patients in different settings, like some are in the ICU, some has been dead, some was ICU, but they have been recovered. But ultimately, with the ethical validation and etc., like about 30 data was accepted in one of the Nature paper, and we showed that how we, from a wealthy, from a healthy person to a COVID-infected person get affected by the other opportunistic bacteria and viruses. So those who are interested can read the paper, it's available. And the second work is going on at this moment. So we found that antimicrobial resistant, what we said, the resistant to antibiotics, is basically a massive issue throughout the world. And in Bangladesh is hugely massive. So for example, when in UK I go to GP, there is a big signboard is written there that don't take antibiotics, it's not needed. And doctors are very cautious giving antibiotic. But in Bangladesh, just you go to pharmacy, you can buy an amoxicillin without asking anyone, not a doctor, nobody, people are. So we need to, not only we need to study that, but we need to make aware also that how it is affecting us hugely. So we have one study in 2018, 900 patients were admitted with the resistant to antibiotics, and 400 died. So it's a massive things that needs to work on. And genomic scientists in Bangladesh is taking it seriously, although we have very low resources. So we have done 180 bacterial whole genome to find the AMR genes, and it's a good work going on. So for the collaboration BCSR has done, and also you'll be happy to know that they attracted a lot of good grants too. And although it's a government organization, but it's having outside grant with the collaborative proposal with Nottingham University. We have done one work, and another is on the process. We have King's College, we have EBI, and there are a few other new collaborations is going on as well. And what I want actually, not only foreign collaborations, people from computer science, statistics, mathematics background, if they want to solve a problem, what is good to, I mean, to solve a human disease and human problem is the best one as I can think of. So it's just computer science people is just not the software, developing software. I think that there is a huge problem to solve in genomics area. Basically, biologists doesn't have much idea about what they will do with so much data. So there's a lot of work and a lot of collaborations we need internally in Bangladesh with different universities and who are interested on getting involved. So some future plans of BCSR, you can put a lot actually. I'm not going into like description. So for the audience today, what I see that our from computer science and biologist background, not only computer science, a different area of mathematics, statistics, and whatever science is, if someone is interested and want to get part, and we need a lot of bioinformaticians, and we know that solving the genomics problem is a huge multidisciplinary works. We need doctors, we need biologists, we need mathematicians, statisticians, and all kinds of people, machine learning. So we need a lot of internal collaboration in Bangladesh. I put some boxes is to understand that how data scientists can be involved in each boxes. If you can think about, I'm starting from sequence assembly. It's a purely after getting the data is a data science jobs. Gene discovery, if you think about you will work with a lot of Bangladeshi people's data, you'll definitely find a new gene when something is not matched in with the current repository. Then think about it and put through that gene separately. Definitely we'll get Funi genes in Bangladesh. It's all data-related work. Structured prediction mainly in protein-related area. It's data-related work. Gene expression analysis is completely software scientist job. Even in drug design, there are a huge area where software and computer science play a huge role. Biological data repository is like, you can think of a building infrastructure from the hardware perspective for the repository. Personalized medicine is a lot of talked about area, but there are a huge amount of work. So all the boxes you can see here, there is huge amount of work, just not the biologist. It's us from different kind of science background. It's a very simple workflow how actually data works. If I give practical examples, if for example, you take the COVID data, the sample has gone to the machine. From machine, it produces data. That data needs to go into the data repository. Then start working on that to make a copy, use that software, this software, make the pipeline. So it's a very basic data pipeline, but you get the idea that huge amount of work is needed from a data scientist. We call it central dogma. DNA makes protein, protein makes, DNA makes RNA, RNA makes protein. So basically protein is the, you can say, the building block biologically of how we operate, from our talking to our organ functioning. So basically in data perspective, if we see, we have a DNA sequencing, we have RNA expression array, exon array, microRNA array, we have a protein level identification, any change in the protein. So it's like, if we say in 3 terms, that in DNA, like one group of scientists can easily work, I mean, it's a huge amount of work is there. In RNA, is another group of people can work, and a protein like another group can work. I mean, there are a huge amount of area from even our data perspective that we can work on each area of the central dogma. Here I put it, typical bioinformatics pipeline is starting from DNA RNA sequencing to get the drug discovery. But when I say typical is basically, it depends on actually what experiment you are designing. If you design an experiment, say for example, you will get inside of a autistic person, how their different kind of gene expression works. Is there any difference from the normal person? So that means your first target is getting the sequence, and last, the last output of the pipeline is that what actually you will be finding the difference in that autistic kid. So from all the bioinformaticians, you will always find that they are actually based on their experiment, they are designing pipeline and make that pipeline available who will be working on this kind of area. So a lot of collaborations going on, is basically new kind of area, you can say, and all the pipelines that's available in the open space is very important for the researchers. Lots of talked after things is personalized medicine. So what I see that is still in very early stage everywhere. The main reason is not that technology is not there, technology is there. And also the research scientists are there, but it's very costly. We don't have enough people to get the medical knowledge to give the personal support for the patient, not even in the Western world. So I mean, it's a very early stage talking, but you get the idea that we get a sample in real time from patient, and then ultimately we suggest them what to do or put them under intervention, that what can be done for a particular disease or any changes in their mutations or gene functions. Here I put again, as you can see, I'm a lot more emphasis on our like how data perspective we can be involved here in bioinformatics. You can see all the boxes I put through. 80% of them is actually comes from the different kind of science, like statistician, mathematician, data processing specialist, data analysis annotation, database specialist. Even writing a good interface is very important for the biologists, because they are not, most of them are not that much equipped to use non-friendly like Linux-based software. So they need to have a good intuitive user interface that we can provide them. I finished my first part of talk. So in second part, I will put through very simple example of algorithm I have chosen myself. Then I worked on until to the end, and I worked for the. I made the software so that it helps on the real problem. Before talk about the circular string, I want to say that why I think about the circular string problem. There are a lot of bacteria and viruses. Those are circular in nature in terms of data. So when you take the genome, you know, the genome is just 4 characters, A, G, C, T. So when you take huge amount of data, and some virus bacteria has got circular in nature, that means it can start from anywhere. So it's basically not not an unknown problem for the mathematical community. For 100 years, people knows about the circular string. But the issue I found that the kind of software has been there, and the kind of algorithm they have used is very slow. So I started working on how I can improve with the current mathematical knowledge, as well as using my software development experience to optimize things. Set aside the circular virus, we are coming back later. So now let's see what circular string is, and what kind of algorithm is available there, and what improvement can I make and do the software to solve this problem. You can see from the slide that circular string is actually just a string that can start from anywhere. Go to the last paragraph. So for example, I put a string A, B, A, B, A, B, B, C. Very simple example is first rotation will be, it will start from B, and A will go to the N. Then the second rotation is, it will start from the A, BA will go to the N, and so on. So you can easily imagine now that it's, if you do exhaustive algorithm here, just to find a circular pattern in a big string, the complexity will be n squared. So think about biological data. If you're just searching it in a like 100 terabyte of data, what will be the scenario? So, I mean, without linear algorithm, it will not work, number one. And even with linear algorithm, it will not work if you cannot jump the data. So it's just two kinds of circular pattern matching I was thinking of. One is the exact pattern matching, to understand at first myself that if it works or not. And in biological world, exact pattern matching will never work. So the reason is, you are taking biological data, it has got error, a lot of different kind of errors. So you have to take into consideration all the mismatches, like X percentage of mismatches. Otherwise, on biological data, my algorithm will not work. So then I started finding the literature. I found that, okay, both algorithm does already exist in linear time. And I run those algorithm in the real data. And I found that, yeah, it's still slow. So there is no data jump or filtering is there. So I devised some very simple observation. If you think about a circular string, and if you put the value on all the data, A, G, C, T, 1, 2, 3, 4, for example, wherever the string starts, actually summation of the numbers on the exact circular pattern matching will be the summation of wherever it starts, as long as it ends with that circular string. So it doesn't matter. Simple observation actually give you a powerful tools, and it is very simple to compute. Now to make it more so that we have removed more false positive, think about the distance, absolute distance, just take the positive. Then you're putting another filter very intuitively, and it will make faster. I don't know yet it will make faster or not. So let's see when experiment done, how much faster it is. Simple, powerful things do. Third is, instead of taking absolute distance, now take positive, negative into consideration as well. So for example, it's going to 2 to 3, that is -1. Then it's going to 3 to 1, that means 2. So -1 plus 2 equal to 1. In this way, then this should work the same as well. The reason is it's circular. Wherever it started, it should the same. Similarly, basically, I'm trying to making it harder, but with very simple calculation, so that with in the big amount of data, if you do this simple calculation, it will not lose anything, but you can actually do the jump. Then fourth one is the ith distance, like the character. For example, G is in particular distance in the circular string. Wherever it starts, from G to G, it will have the same distance if you think about the whole string. Same for modulo. It's just another another operation I introduced. So all the basic stuff I could introduce. Then I came up with the Excel. I tested all of the simple scenarios on the real biological data. What happens? Okay, so far I was talking about my observation just in exact method, exact measure. Now, if you think that biological data has got K mismatch, so for example, on these data, we'll consider 10% mismatch, 5% mismatch, or even 15% mismatch. Now we'll see that how the algorithm looks like. So basically now we'll have an upper bound with the -k, we'll have a lower bound with the -k, we'll have an upper bound with the +k. So similar 6 observation, just I am putting just with the lower bound and upper bound, and in the middle is the absolute one. So the reason the lower bound or upper bound I'm doing, so anything outside that, I can actually jump in the data, so that these data is not part of, for example, I am just searching one signature, circular signature in a big amount of data. So if I think that I cannot jump hugely and I need to actually linearly go to the end, it will be a disaster. So that's where jump helps this algorithm a lot. We'll see the result later. These are all the example. I guess you are already clear what I wanted to say. Is the very layman type example that how I get the value of a different filter and how it works. It's not very necessary to, so I'm just directly jumping to the algorithm. So you can see that from exact pattern matching, you will have 2 algorithms, very simple algorithm. One is your signature. The 6 observation I have put, 6 observation, I will make a very simple pre-processing the signature. And then for exact, I will actually run through with on the text. So basically, at first I made the signature for my small string, or it could be even for Arcia, it is like 1.2 kilobyte. So the after in this signature is all simple observation for 6 observation, and one of them is the particular data it has got. It needs to define with the different array. I'm not going into the implementation. Basically, just from the algorithm, you can see that how easy, if someone even doesn't see the algorithm, they can easily actually write the program. So signature is pre-processing, then run this signature on the whole text. Just I propose myself the way I have written the software, but someone obviously can do the tweak and do their own way. So first I have the signature and run through the whole text. And the same, as I said, that exact pattern matching is important for the mathematics perspective, but for biological perspective, exact will never work. That has to be approximate. So for approximate, I have the same similar 6 observation. Then I have taken into, with the K values, into consideration that I am jumping the data based on my lower bound and upper bound, and applying it with the actual data. Like I have the text T and I have the pattern P, and the whole pattern P will be run through the text T. Just one, yeah. So I'm showing the result now. If you see the second column, there's the existing algorithms timing. The third column is the my only one filter timing, and it didn't improve just point something. It clearly just with the real data, some simple powerful observation, giving me 2 times, 3 times, 3 times, 3 times. I mean, that times faster. Then I have put, when I put all the filters in, you have seen in the fifth column, it's giving very powerful result. So it's the 5 times, 8 times, 7 times, it's like this. So I put a lot of different kind of in the left-hand side, the size, and you can see 4th and 6th column is very, very powerful, what result I'm getting. Yeah.
So actually, we need to finish in 1 minute. I sent a message. Yeah, sorry for that.
Sorry for that. I'm done actually. So this is the software I made for the people, and it's been used for this particular program. Okay, thank you very much. Thank you.
So thank you so much. So maybe we can, if anyone has any question, then maybe you can take 1 or 2 minutes to ask some questions. So the first question from the Professor Siddiq.
Yeah, so it was really nice to know that in Bangladesh we have these world-class facilities. Just my question is how we can get access to these resources. What is the formal procedure? Say if I have to do say genome sequencing for 100 people. So how do I approach?
Okay, so basically it's very straightforward. The reason at first I did it in BCSIR, you know that BCSIR constitutions allows directly to work with the industry. It's called Bangladesh Council for Scientific and Industrial Research. And also they can easily collaborate with any outsider. Based on Bangladeshi structure, you know that it's difficult, but for BCSIR it's very easy. That's why they are doing a lot of collaboration. As a researcher, what I feel that you need to do, you first design your experiment, that what you'll be do with it. Better go into the collaboration with them, so they will produce the data. Sometimes even if it's not enough funding, and government is always doing the sequencing, so they can help you out with that. But the way Nottingham University has gone, they uses that infrastructure. Also, they take researcher from BCSIR on board. They did collaboratively, and they attracted huge fund. I mean, first project was 250,000 pounds. So it's not like a very small grant. It is a big grant. And they work on the cholera strain changes in Bangladesh. And there are a lot of partners as well, like ICTTRB, then North-South University. There are different partners. So you can design a big proposal or whatever kind of work you want to do, then propose BCSIR. There is a way, and you can work collaboratively with them. And they are also scientists. I mean, they're not like government officers, so they're working hard in the lab. Yeah, thank you.
Yeah, and just a little, question linked to it. So how much will it cost? Say, if I go for genome sequencing for, say, 100 samples, how approximate so that we can estimate to do collaboration?
So basically, it's all different kind of sample and machineries. If you think about the bacterial and virus genome sample, it's very tiny amount of data. If you think about the whole human genome, so roughly I can tell from the head, it could be like 10% plus minus. Think about the only reagent cost. It's because it's government institution. You don't need to give profit or anything. You just need to give the reagent cost to them, or you can buy reagents. So for example, 48 human genome costs like roughly $10,000. So whole genome. So basically, you can provide them just the reagent for the machineries, and the data will be ready for you. So they are very, very collaborative, and they also want to produce a lot of data. So
thank you. This is very useful. Thank you for this opportunity.
Thank you very much. Thanks.
Okay, thank you so much. So I have a small question. So you mentioned that for the circular DNA, you developed an algorithm.
Yes.
So I know that there is an algorithm BWT,
yeah,
Barrow-Wheeler transform. What is the difference between that one? Like, what is the change with the BWT?
No, basically, I didn't consider that. We consider based on the literature, basically what people used first, what is already fast there. Then I have taken that one. If you see my slide, the second line, elapsed time of SC as MF simple K, it was on the literature, it was giving the best result. So I worked on that, so I need to improve this. I didn't actually consider it because I came from software development background. I wanted to actually put through really useful software for the biologists. So I didn't consider what is in the literature says that already inferior. So I can tell you that all other algorithms exist on that time. ECMSF simple K was the best one, and I actually targeted that and I improved.
Okay, thanks. Is there any question? Okay, thank you so much. Thank you for your nice presentation. I think people will understand many genomics matter of Bangladesh, especially for the COVID-19 related genomics and the metagenomics from the microbiome and other like species. Thank you so much. We are finishing the session, but before finishing, maybe
hello, sir, am I audible to you?
Yeah, so you can share the
Thank you, sir. Thanks for your cooperation. Thanks the speaker for presenting a nice speech to us, sir. We have something to share with you, sir. We are going to share something for you, the speaker, and this is.
Shamir, you need to unshare your screen, so that he can show the certificate.
Yeah, sure.
Yeah.
This is the certificate from the organizing team for you, sir.
Thank you very much. Thank you. And thanks for the opportunity. It was lovely to speak to the people who actually the audience, especially for the BCSR, and hopefully a lot of students can contribute. Yeah. Thank you.
Yes, sir. Thank you, sir. We believe we are the young researcher, and we will, inshallah, one day we will also present like yours. And it's inspire us. Whole day we have listened your lectures and acquired some knowledge from your speeches. We think we will use these knowledges in future. Thank you, sir. And we believe all of you will participate in our ending session. And ending session will be conducted by the Shahriar Shetu, sir. And for this session, we have Professor Dr. Petrolio, who is the General Chair of MEET 2022, and also the Muhammad Ali Moni, sir, the General Co-Chair of MEET 2022. Thank you, gentlemen, for conducting the rest of the session. I am requesting Shahriar Shetu, sir, taking the floor. Thank you all.
Thank you, Rafiul Islam, to give the chance to conduct this session. Now I am requesting Professor Atikur Rahman Ahad to share his feelings about MIT 2022. Thank you.
Thank you very much. I was not supposed to talk, but actually this is the first conference in this university, and basically led by the person we can see here, that he is the main man for this conference. Worked hard for a year relentlessly. Of course, many people helped. It's always the case. But this young guy, I mean, conducted so many things and worked so hard, and definitely made the team and realized this. So this is excellent indeed. And our researchers, like, I mean, top people from all over the world, especially people like Pietro Leo. I mean, Pietro, to be in the conference committee helped us a lot, because a big guy like him as the father figure for a conference, for a new conference, it's extremely important. And we have lots of speakers who agreed upon to be part of this conference. That is also wonderful. Locally, I must thank the Honorable Vice Chancellor of this university, I mean, to support this conference, and some local industries to sponsor partially as well. That is really lovely. And behind the scene, always the program committee work hard to make a conference successful. So we had lots of papers, but again, the core committee members, they tried their best based on whatever papers they achieved, and deciphered the better works. So this is also very good. And I'm proud of the MEAT team, and we hope that with your collaborations and supports and more active participations, we can organize it in the future. And I recommend to organize it in every 2 years, because that would be relatively better to arrange without much load. So maybe 2024, we can do it, and we can confirm that our legendary persons and like Pietro and others can be in the conference in person, so that they can enjoy the beauty of Bangladesh and Noakhali or another venue. At the same time, inspire many young people. That is, I mean, very important. And we thank all you for kind support. Thank you so much. It's a great pleasure to be part of this conference. Thank you.
Thank you.
Just if I can add one comment, I think that I am impressed not only by the skills, but how friendly and nice are the people. So this means that you are able to create and cultivate a beautiful environment for research and for exchange and discussion. So in some sense, this is something that should be continued, and this will be particularly good to bridge people in Bangladesh with people from Bangladesh who are working outside, and they are bringing experience so that for the growth of a country. But this should be inspirational to all the people of all the other countries, because this has been a very skilled, but also full of welcoming messages and very, very nice people that have discussed things. I'm very, very impressed and pleased.
Thanks.
Thank you, Professor, for your nice speech. And I am requesting General Co-Chair, Dr. Ali Muni, to share his feelings about this conference.
Thank you so much, Shetu, for giving opportunity to talk something related to this conference. Actually, it is really very good conference, especially for useful for the young students and young researchers of Bangladesh to make the bridge, as mentioned, Pietro Leo, with the people in other country. Also, they can understand the research trend that are happening in different, like in current environment, like in current situation. So I think that especially in the organizing committee, the Shetu and other people, young people, they have taken a lot of responsibility. And I talked several times with Shetu and other like young colleagues from the Noakhali Science and Technology University. And I thought that it is very hard to manage and maintain these big conference, international conference, but it is successfully completed. It's really amazing conference, and with the in addition to the like Atikur Rahman Ahad Bhai, I would like to say that you should, like, not you, maybe the Noakhali Science and Technology University or other organizing committee can run the similar conference in every 2 years, in addition to the other international conference in Bangladesh. So it is fruitfully and successfully completed, and everybody is enjoying, I think, and especially the authority from the Noakhali Science and Technology University. I hope they have supported a lot. That is the reason it made successful of this conference. And there are other people, they are involved and continuously discussed. Even I was the organizing secretary, but I could not attend several times. So I apologize for my lackings because of time constraint and the responsibility in my current in the university. So on the other hand, like Professor Samsul Arifin and Shamim Kaisar, like Atikur Rahman Ahad Bhai, all of these like people are working hard to make this conference successful. Not only this MIET, also the other international conference, those are holding like in different times in Bangladesh. They're trying to give their whole effort to make the successful of this conference. So best wishes all of you, and I hope next time we will enjoy this conference and we will attend physically in Bangladesh. And I will request Pietro, if he is available at that time, I will request you to visit Bangladesh at that time.
Yes.
And I hope he will enjoy the country and the people and the entertainment and the everything of Bangladesh. And thank you so much.
Take care of you all. I have to rush to the hospital.
Okay.
Thank you,
so
Professor Petrolio, to stay with us. And
so maybe he is going to hospital because he has to urgent leave to go hospital. Yeah.
Yes, Professor Petro, thank you to staying with us for a long time and your nice lecture. Now I am requesting Professor Samsul Arifin to tell something about this conference.
I thought Professor Petro already left for some reason. Actually, we had to hear something from him. I said a lot yesterday and day before yesterday, so it's anyway. Thank you very much, organizers, as mainly Shahriar Shetu, for your great effort with your team. It's a very good event. I had the opportunity to physically present in last 2 days, and it was excellent because in every, that means programs, food and every other issues, it was fine-tuned, and the presentation, the venue preparation and all other issues, actually it was really excellent. Yesterday I mentioned me and Shahriar Shetu were discussing a lot. Even we took our dinner together and with our volunteers. I told we shall take our dinner with our volunteers at the last moment. So Shahriar Shetu, as our Honorable Atikur Ahad Bhai, Moni Bhai already mentioned, that means overall potentiality. And actually we need many more like Shahriar Shetu, and we hope in coming days we shall continue this conference. And as Atik sir and Moni Bhai already mentioned, it will be better to run it in alternate years. And we hope it will have a very good, very big impact among the, that means our young researchers. It attracts a lot of young researchers and hope it will continue. I should mention the name of several persons. Atikur Ahad sir, actually, how can I say how he can manage so many times? Actually, it's a big issue. We feel proud for you. Atikur Ahad sir, his contribution every time he was knocking, he was mentioning, and I was traveling in that time in some other issues, what type of suggestions, and actually all these suggestions are very much valuable. Our Honorable Moni Bhai, you are always with us. We hope you are coming back for a few months in Bangladesh in December, and we shall have a very good time in that time. So thank you, Shetu. And as well as in my closing speech, I mentioned the generosity of the Honorable Vice Chancellor, Treasurer Sir, and Pro-VC Sir. What I found, actually, I should mention there, when Shetu and Iptika, they were providing the budget and something, they were always positive. Actually, that is not very common in our universities, whether it is private or public. So Noakhali Science and Technology University has a very good chance to be a pioneer among the science and technology universities, at least. So they are in the right direction. And we hope in coming days, we may arrange it in some other venues. It may be declared by our Shahriar Shetu will say something in this regard. So thank you all on behalf of Technical Program Committee. Actually, I am now in a university, not in my, so I have to take classes as well. In the morning, I had classes almost, I traveled from NSTU and reached here around 6 p.m. 8:30, there was classes almost whole day. So actually, I'm extremely sorry for my absence into this programs. Sorry. Thank you very much. Thank you. Thank you all. Shetu.
Hello. Can you hear me?
Yes, Shetu.
Thank you all to express your feeling in this MIT 2022. And now I want to tell about the next tentative events of this conference. We are planning to organize MIT 2024 at the 3rd week of September 2024. So thank you all advisory committee and organizing committee plus technical committee members to assist our young researchers who are trying to establish a potential something research community at Noakhali Science and Technology University. So hope we will organize MIT 2024 more successfully to learn from this event. So thank you all.
Thank you.
And we want to close this session. Thank you.
Thank you. You can stop the recording.
Okay.
We may, আমরা আতিক স্যার, আমরা মনে হয় কিছু সময় একটু বসতে থাকতে পারি। আপনি তো মনে হয় এখনই, মনি ভাই কেমন আছেন?
জি, আছি, আল্লাহর রহমতে ভালো আছি।